Hello, wonderful people of the internet. Welcome back to another episode of Leos Labs, Shadowmishia, and anyone who might be lurking in chat. Hey, thanks for being here. Give me just a second to update my camera really quick. I think there's a video audio desync issue. Right, so I'm starting an hour late today. Look, here's the thing. I've been very consistent for the past few days, or I've been trying to be very consistent with my stream times being from basically 2 p.m. to 8 p.m. every day. Today I messed up. I ended up starting about an hour late. Currently it is 3 p.m. The reason for that was simply because, well, my wife was on a business trip last week, so we missed Thanksgiving. And this morning we decided to cook a nice meal, lasagna actually, and then she had a conversation with her parents afterwards. So I don't know, it just ended up being, we were hanging out together, and I just thought, that was more important than starting stream right at 2 o'clock. That's what I thought at the time. I mean, maybe I'm wrong, but I thought it was important. MRS, hey, how are you doing? Again, we're going to be doing basically the same stuff we were working on yesterday, the 4D Galaxy simulation stuff. So what I realized was yesterday I was when I started stream, I was maybe a little bit bored of the Galaxy simulator because, well, after we did the 4D results, they just weren't that impressive. And I was kind of afraid that, it just wasn't going to work out, But now I kind of realize that, at least for my purposes and the purposes of the research that I want to do, the 3D sims are actually more valuable. So because of that, I feel like we're going to continue doing the n-dimensional Galaxy simulations and see what we have to do. The GitHub CLI client, is that not just... Oh, the GitHub CLI client is different than just Git, right? Because I don't know how the GitHub CLI client works. Okay, so we're going to do a quick couple of Algorithm Archive PRs, and then we're going to move our way back into the Galaxy simulation. If you guys are here specifically for the 4D Galaxy, don't worry, we will get to that. It's just going to be about an hour until we do that, and then we'll spend 4 hours on it today, and we'll see where it goes. So let's go ahead and hop into it. So we're going to go here, go to the Algorithm Archive. There, let me make this across all desktops. And let's go. So there's one big PR that we're working on, but I think we can go to PR number, 941, I believe is the PR number. Let me go ahead and check. And I believe that one's also ready to go. So let's do pull requests here. 942, was this one it? Wait. 940, this one maybe. Okay, what do we have here? So this one should... Now that People Warrior and I have decided on Discord here to give up on trying to build x86-64 assembly on Windows, the linkers seem to be outright ignore the no pi option, as well as the double no pi option. Okay, so I think this is probably ready to go. What I'm going to do is build it locally just to make sure it works, and then we go from there. I got to be honest, my algorithm archive time recently has been pretty much only working on the... on auxiliary PRs that I'm going to put forward, like the Fractal Flame chapter and stuff like this. But also like the stuff I've been showing on stream has predominantly just been the Metropolis algorithm. So I haven't been keeping up to date with this stuff exactly. So what I'm going to do is pull it locally, check it, make sure it's working, and go from there. Let me open up a new terminal here. Huge over there, and a new terminal here, there, and let's cd into projects, algorithm archive. All right. I guess before continuing, since we're kind of in that mode where we're updating people on different things, let me just talk really quickly. This is not going to be a YouTube rant. Again, I promised I'm not going to do a YouTube rant anymore. Just want to update you guys on what I am planning to do with my YouTube, what I'm thinking about doing with my YouTube content in the future, and I'm interested to see what you guys have to say about it. I think about YouTube too much. Like, honestly, it's always in my mind. And last week, I kind of had the idea that, look, if I'm going to spend time video editing, it's probably better served spending that time doing actual research, right? That's what I was thinking about before. But after the 4D Galaxy Sim kind of blew up and we realized, actually, this probably isn't going to work, it kind of dawned on me, and I knew this before, but it dawned on me that if I only put out a YouTube video when something interesting happens, then we're only going to have a YouTube video like every 2 months. Because what does interesting mean? To me, it means you've published a paper. And the fact is, when you publish papers, a lot of the stuff that you're talking about is not actually interesting for a general audience. It's interesting for a group of researchers who are interested in the same topic. So how exactly do you do open research in a way that's actually engaging and interesting? I don't know. I'm trying that with the Twitch stream, but I think on top of that, I need to figure out a way to make regular YouTube content. Not the stuff that comes out maybe once every other month, but stuff that comes out hopefully maybe every other week or every week if I'm really good about it. So certain videos that I could potentially make is the one where kernel abstractions broke when we were trying to do int32 of I, for example. That was an interesting problem, completely broke. Another one, for example, could be the blind programming challenge. Another one could be how, I failed miserably at creating the n-body simulations, all the bloopers, stuff like this. And then we've, of course, got like the world fastest, world best, like all the actual research videos. So anyway, the reason I'm talking about it here is because there is a fear, and it's just, I know it's an internal fear, but there is a fear that if you publish a bunch of videos that have content that people don't like, they're not going to come to watch. They're not going to come to watch more content in the future. So that's kind of what you have to balance, right? So the two things you're balancing are, one, the interestingness of each video, because the more interesting the video, the more likely people come next time. But also the cadence between videos, because if you only put one video out every 2 months, people are just not gonna remember who you are, and they're not gonna click on your next video anyway. So that's kind of where I'm at. And the fear is that if you put out really big videos that are like, oh, this is amazing, we spent months on this one video, but you have all these other videos that are kind of in between it, like Blind Programming Challenge, which is just like a one-day thing. I don't know. So my question is to you guys, when you guys are watching YouTube content, what do you actually like? What do you care about? Do you care about the person? Do you care about the things that they do? And this is kind of my open discussion because I really don't know. I had this discussion on YouTube a few weeks ago, and basically everyone said, look, they actually would prefer more like conversational approaches, kind of like what I have on Twitch. Anyway, all that said, that's my final bit on YouTube. Just want to say I'm currently thinking about making a video on this one, the blind programming challenge and bloopers and all this kind of stuff, just to see what people have to say. Now, everyone in chat is talking about the race to type E in chat. Here's what happened. Every time after I put the live notification here, someone below, usually Cosmic, but other people as well, will type in E. Now, today, the moment, like literally the nanosecond, I typed in the live notification, then there was 3 E's in chat. It was insane, absolutely insane. And so I'm thinking, I almost thought I should have trolled you guys, because I actually saw in the chat, I saw Neon Litz was typing. So I saw someone had preempted an E. And so I was like, ooh, maybe I should just like write something that's not the, write something that's not the actual notification. So we had people who had pre-typed E's. That was really funny. I really laughed at that one. Actually might have been the reason I was kind of late to stream, because I thought it was really funny. But also I had to run upstairs. I started streaming at 3 or whatever, but then there was like a 10-minute delay before actually stream started because of various reasons. Anyway, what do we have here? Was just thinking how you said open research yesterday. I love this concept. Yeah, we're doing our best. The challenge here is not necessarily the openness, it's the engagement. I think doing open research is fine. Sure, you might run into people who are stealing your research, but the engagement, getting the community involved and actually using the platform you have on social media to make the research better. That's kind of what we're working on. What do we have here? You should do weekly videos on the Formula E race. What's the origin of the story? Basically, for some reason, no one really has any idea why. Cosmic47, it is Cosmic, yeah, 47, just decided to start typing E after I put the notification in the channel. Again, no one has any idea why. It just happened. And then after he started typing in E, other people were like, oh yeah, okay, yeah, we can follow suit. And so now we actually have a role on Discord, which is the first to E. And anybody who gets that first slot with the E, they'll get a special title, which is just the first to E. I gotta be honest, I don't really know why. But at the same time, like, I'm not gonna, it's kind of fun. Like, I think it's funny. And I'm happy for it to be a meme. Like, this is one of those things that, like, if a meme appears in your community, you can either nurture it or like squash it out. And it's like, fine, let's just keep it going. Could you explain what is going on in your research very briefly? Yeah, so my research is, in general, a mixture between computational science and computer science. These are two kind of distinct areas. And depending on what day you ask, I might give you a different intro. But for the most part, I focus on, or my research up till now has been in like GPU engineering and stuff like that. And it's kind of something to take ordinary processes like n-body simulation, stuff like that. In fact, let me just go ahead and put an n-body simulation on screen. Projects, Galilee, MPV. I think there's like 5 people with the role right now. All.mp4. Sorry, aux. And then we're going to do MPV all.mp4 loop. All right, so we'll just have this playing in the upper right-hand corner, left-hand corner, like we always do. Perfect. Good. Move this up here. There we go. Move this down a bit. There we go. All desktops, why not? Okay, move this down here. Ooh, okay, I'm struggling a bit. That's okay. Right, so if you look up here, you see a basic n-body simulation. So an n-body simulation is a simulation with n bodies in it, where bodies here are little particles moving around. So each of them can feel the force of gravity of every other particle in the simulation. Right now you see it in 1D, but eventually, in just a second, you'll see it in 2D. And the idea here is that all the particles are feeling each other's forces based on mutual gravitational interactions. This problem is very easy to solve. Like creating an n-body simulation is pretty quick. Doing it efficiently on the GPU, specifically with parallel or distributed architecture, is a pain. And so what I typically do is I focus on taking these problems that are relatively easy to solve and making them much faster on hardware where they're not typically supported. That's what I like doing. And so in some sense, it's computational science because that's what the n-body simulation is, but it's also computer science in that we're using the tools that computer science has created to speed this up. So that's kind of where I'm at. I like, when we talk about like how to make this engaging and stuff like that, part of that is doing the Twitch stream, making sure everything's live. But the other part of that is doing things that are somewhat clickable, like things that people, will look at and they're going to be like, wow, I learned something from that. I liked that. Even if they don't understand all of the little details, they can look at it and be like, oh, that was actually quite cool. I'm happy I watched that type of thing. I think it comes from other streams. I know that chat spams E and Technoblades chat sometimes. And of course the E meme. What is the E meme? I don't know what that is. Wait, is that the one where it's just Lord Farquaad with an E? I never understood that one. I don't get a lot of memes. But that one in particular struck me as one that I really don't understand at all. I don't get it. Why? What's going on? Anyway, let me move over here, move this down, and let's start with some algorithm archive PRs. So, before getting into the 4D Galaxy simulation, which is, of course, the big thing we're doing on today's stream, we're going to do some algorithm archive PRs because, again, it's really good to make sure we do at least a little bit of algorithm archive work on every stream. Very interesting. I saw your video on billiard simulations. Was it you? I don't think so. Which video on billiard simulations? The billiard simulation, the only billiard simulation that I've actually done was for a molecular dynamic simulation of Maxwell's Demon, which I accidentally deleted on my channel, so that video is no longer existing on my channel, which kind of sucks. But outside of that, it's... the only billiard simulations I did were for the Julia Computational Thinking class at MIT. So that's the only other billiard simulations that I think I've done publicly. Okay, so let's go here. Let's take a look at the latest changes, and let's try running it. We'll try running it twice, once without Docker, and then once with Docker. And if it runs, I'm actually happy with it. I think we can go ahead and merge it. Let's grab this guy. Grab this guy. Perfect. Okay, so we have this now. So how do I actually run this for the... Can I just run scons? Okay, is this building it? We'll look over that again, but it was a video on how to make them efficient, so maybe it was not you. Oh, probably wasn't. I gotta be honest, this is my first foray into making things efficient in this way. I got a feeling that this just did C and C++, but did not do... Wait a minute. You can use some math approximations to trade off accuracy for speed for simulation. I don't know how you would optimize it specifically for the GPU. Yeah, so that's something that we will probably... Yeah, that's something that we'll probably look at maybe today. It depends on where we go. But I'm hoping actually to look into different ways in which you can make these approximations, in particular using octrees. That's one big way to do it, but there's a bunch of other ways to do it as well. The nice thing here is that it actually bleeds into another area that I'm quite fond of, and I really have no explanation for why I'm so fond of it. But the other area is called color quantization. It's an area in computer graphics where like you literally just remove color from an image, or you use like for example, if you look outside, you take a picture, you could have thousands of colors in the image, but you can only use 256 colors for a graphics interchange format file or a GIF or GIF, depending on how you want to pronounce it. And so to remove the colors so that you can compress it, that's a key problem with computer graphics. Okay, so let's just do the build on build ASM 64. Did that work? Is up to date. Okay, so we're going to cd into build. Build. ASM, ls here. Okay, good. So we have everything. I'm just going to run stuff really quick. So if we do Euclidean algorithm, sure. Forward Euler. Segmentation fault on the forward Euler. I don't know if that's a problem with the x86 code or the forward Euler. /Huffman. I mean, most of these are working. Monte Carlo. Sure. Percentage error, fine. /Kulituki. I actually don't know what that's supposed to output it. You need to clean it before you rebuild it. So is it scons, what is it, scons clean? You use clustering algorithms for that. Yeah, definitely clustering algorithms. That's kind of what the octree stuff does. Okay, let's do an ls here again. So Kulituki Euclidean algorithm. I think I did Euclidean. Forward Euler, for some reason, is broken. /tree traversal. I think that's correct. And then we're going to look at relay integration. Okay, in principle, this is working. However, the forward Euler method is broken for other reasons. Okay, good. Yeah, I think I even remember that issue. Let's see, what do we have here? You need to rebuild it. A couple months ago, I was looking on rigorous computations of dynamical systems using interval arithmetic. Any chances of such exact approaches experiencing dramatic speedups as well? This is interesting, and I don't know. I don't know the best. I don't know about these areas so much. Like I've only seen them in passing in different people's research. I haven't seen it like that. I haven't seen it in very many places. So in principle, it could be a unique way to solve the problem. In particular, I was thinking about maybe having a way in which you could basically create what is essentially a potential field, like an affine map or something, that would basically say if your particle is at some position, it moves in this way. So every time step, you basically just update your map or your like new potential of all of the particles together. Like there's a way to get this to work. I don't know. There's a way to get this to work. I'm not really sure how, but I think there could be some interesting interesting applications to like analytical fields via fractal flame methods and stuff like that. And to clean scons C, thank you. Let's go back a directory, scons-c. Okay, so now I'm gonna go into the Docker container. This is where I need some help here. So sudo systemctl docker .service enable. Probably enables before this. Enable. This is gonna work. Create symlink. What is it? It's docker dot history grep docker. I misspelled grep. I'm sorry. I'm failing. Is it not docker.service? Is that what I need to enable? Is Docker up? How do I run this? I suck at Docker. Every time I have to look up the commands. Every single time. There's not been a single time that I've run Docker that I've understood how to use it. And I know it stinks. It stinks because like I know like it's super useful, but I'm just really bad at it. Docker container, Docker build, Docker create. What is it? Let me go back over here. I want to build it again in the Docker container. So I'm going to go to pull requests here. We're going to go to the closed pull requests, and we're going to look for Docker. Oh, here we are. Add publish Docker file here, and then we should be able to test it. It should mention it. Docker run this guy every time. Okay, let's give that guy a go. Right, because it's already available every time, every single time. I suck at it. We need to put this in the We need to put this in the, what is it? The user guide, the how to contribute wiki. Not C-V. Can it create Docker daemon? I knew it. What am I looking for? Docker Arch. It's not docker.service then, it's docker dot... It is docker.service. What did I type? Sudo systemctl enable. I should have done start. All right, let's disable it. And now we're going to do start docker.service. Okay, so now I can try running this. Perfect. It's denied. 1 second. Unable to find image, this guy. What do we have? So I should just be able to Google this, right? Thanks for that, Fabus. So let's go here, paste this there. Of course, it's not found. I should not shell for ZSH, but in ZSH you can type sudo systemctl and press the up arrow and it will go through all the past commands that started with sudo. Yeah, it's just I didn't have that in my history was the issue. 1 second. I think if we go here, where is it? Where's the... Here it is. This guy. Is it algorithm archive language? Okay, let's try this. And run that. Okay, there we go. Perfect. CD into temp. ls here. Oh, right. That's the branch I'm on. And so now I should just be able to scons C. Okay, so now we should do scons build ASM64. Okay, good. Everything seems to work just fine. Perfect. That's all I wanted to do. I'm missing the bash at the end of the command as well. I should not shell for... Okay, right. Control D. That seemed to work okay. So let's go back up here and stop the Docker service. Perfect. Okay. Stopping. Okay, perfect. So that means it does build. Let me check the code really quick. Pull requests. Where were we? Was this a pull request? No, it was this one, and we're looking at this one. Perfect. Okay. In that case, it builds fine. I'm happy with that. I gotta be honest. I looked at the code earlier before stream, and I didn't see anything in particular that was like, stood out to me as difficult. So I think we can go ahead and merge this guy. I'm gonna go ahead and approve this. Let me go up here and go to conversation just to make sure I didn't miss anything. And I think we're happy to get this guy merged in. Conversation here. Scroll down a bit. Okay, so again, the only thing here is that we don't have the Windows build, but at the same time, like, again, I don't think we can. So what happens on Windows right now, actually? So does it just not build the assembly, or does it break? Are you using Qt Browser? Yeah, I'm using Qt Browser. Why? Is there something wrong with Qt Browser? I quite like it, actually. Sure, there might be some issues with it every now and again, but overall I'm happy with it. The linker fails on Windows. So does it build... Oh, good. You're exactly the person I wanted to talk to. So when you build it on Windows, does it completely fail? Like, do you get an error message, or does it just ignore it, or what happens? Is your method special to n-body systems, or what's its generality? Well, we are generally just working on n-body systems, so that's what we're working on. Alphon X0 and Shell C Shore, thank you so much for following. Really appreciate it. Hello, how are you? Okay, so you're talking about the 4D simulator, right? So for the 4D Galaxy simulator, the research focus that I'm actually interested in is an extension to n-body systems. So because of that, we could extend it further. We could do smooth particle, like hydrodynamics or something. But for this particular purpose, we're focusing on n-body specifically now because we're at the early stages, right? You get an error message, but nobody has been able to understand it. There might be a way to fix it, but I don't know. We have no idea how to fix it. Okay, but like, does everything else build for Windows? I guess as long as everything else builds except for the assembly, I guess it's fine. I don't think there's too big of an issue there. I mean, maybe there's a way to like add an exception. Okay, if everything else builds, I'm happy with it. That's fine. As long as it just doesn't break all the other builds. Here we go. Let's go to files changed. Review changes here, approve. Honestly, good work here. Like honestly, I may not be expressing it enough, but this is really good work. So this looks great. Thanks for the work here. Okay, good. I mean, we're slowly but surely getting all the building of the algorithm archive, like, really like up to par. Like it's slowly but surely getting better. And I'm really happy about that. In fact, I wouldn't even say slowly. It's like very quickly becoming like way better than it's ever been in the past. Like we can just build everything like right off the bat. Like it's amazing. I had this like weird, I don't know how to put it, but I had this like weird, idea in my head, that we could just build all the languages together and we could okay, I'll go ahead and submit the review, give you an approve, and then you can merge it. But I love the fact that we can build everything. Potentially we could do benchmarks. I mean, admittedly, the benchmarks aren't going to be perfect, but having a bunch of different languages here really makes things really cool. And it's a really good feature. Like I'm a huge fan of this. Anyway, I'll let you go ahead and merge that guy, but I went ahead and proved it. I'm happy with it. So what are we going to do next? Okay, so also some people might be here and they might not understand what we're doing, so let me go ahead and introduce that as well. We are working on pull requests for an online textbook called the Arcane Algorithm Archive. We'll move on to the 4D Galaxy simulation in just a bit. I just wanted to spend the first hour of today's stream focusing on algorithm archive work, and then the rest of the stream, which will be basically 4 hours, we'll be doing the Galaxy simulations, in particular speeding it up for massively parallel architectures and stuff like this. So what is the Arcane Algorithm Archive? It's an online textbook. The cool thing about the Algorithm Archive is that you can go here and you can basically switch between any of the languages that you want. So in some sense, it's kind of like Rosetta Code in that you have a whole bunch of different language implementations, but it's also more like numerical recipes or something like that. The idea is that we provide you code in whatever language you want, and the hope is that eventually this gets good enough that college professors could, for example, use the algorithm archive or a subset of the algorithm archive for their classes, and it could be in whatever language they prefer. So if they want to teach their class in Julia, they can. If they want to teach it in Fortran, admittedly we don't have too many Fortran PRs, but they could, and that's kind of the goal here, to be able to provide a textbook that works for pretty much anyone, with a whole bunch of different languages. And sure, we're kind of a bit far away from that, but it's pretty cool. Merged, I have a browser extension that removes commit message clutter. That's why I asked. Oh, okay, fair enough. To be fair, I need to be better about the commit message clutter. I should probably, when I do the squash and merge from now on, specifically change the message. So it's just like a one line or something explaining what's been added. Yeah, I should do that from now on. You're right. I've been very bad about that. Okay. Some people really care about that, and I'm not one that cares that much about it. Okay, so we're going to delete that, delete this. Okay, so what I want to work on next is a new algorithm archive PR here. Oh, a new algorithm archive PR here. That is for the Metropolis algorithm. In particular, we've already looked at all the text. The text looks mostly fine, but I want to check the code now. Just to make sure, first of all, it runs, which I have no doubt that it runs. Second of all, that there's an appropriate test for it that we can use multiple languages for, and then we go from there. Let's see. Couldn't come up with anything other than line 147 below. Feel free to throw in some suggestions. What's going on? Wait, 1 second. I'll check that out in a bit. We have to reread the chapter and all that kind of stuff. Okay. So today I'm going to take a look at the code. I know that Amaras probably has looked at the code more in detail. They have a better understanding of exactly what's happening here. But I just want to check some small things just to, again, make sure that there's some sort of test and that the code has some sort of output that people can look at. So let's go here, git checkout master. There was one other thing I meant to do this morning, but unfortunately I just, I would like to say I didn't have time. I did technically have time. It's just I was spending that time with my wife. I'm sorry. But the one thing that I do need to change, and I will hopefully do tomorrow morning, maybe later, but I'll do it soon, is change the algorithm archive master branch to main. It's just something almost all of the GitHub repos are now switching to main. It's the new standard, so let's just do it. It's one of those things that people could argue the switch from master to main was for, not political purposes, but for purposes that are not some people argue it's not exactly a valid reason, but also you know, main is a more like clear, like if you're asking which branch is your main branch, it's very clearly main, not master, right? Like you wouldn't naturally be like, oh, it's a master branch, right? Like that doesn't make any sense. So like in my mind, it makes sense. Let's just go ahead and make the change, especially because it's the standard now. So, okay. What am I going to do next? I'm going to do get status here. I don't know why I did that. Get branch. Why are these all untracked? These are class files, PNGs. What is going on here? JLcheck.png. Oh, these must all be, these just must be for other things. It's for NA politics, which is internet politics. Right. I mean, to be fair, I mean, I think it just makes more intuitive sense. Like, I mean, I know there are all the people who are arguing that, oh, you shouldn't change it. But all those people are saying you shouldn't change it. I think their arguments aren't exactly valid because it's like, first of all, ignoring the politics, like main is just a more clear name for what this branch actually is than master. So I'm like, fine. Like if we're changing it and it makes things more clear, let's just do that. Like, fine, who cares? You know, like, sure. You know, potentially you have a whole bunch of CI issues, but just stick to the master branch then for all the old code, and for the new code, use main. I don't know. It's not as big of a deal as a lot of people I think made it out to be, in my opinion. But honestly, what do I know, right? Okay, so we're gonna do get branch, get checkout this guy, and then we're gonna take a look at the code. Okay. So now let's do, oh, I need to go over here, grab the latest changes again. I might take a look at the chapter again. Yeah, I want to see what he did for that intro. Okay, so let's do here, write and quit. So let's go into the metropolis.md file. We're going to cd into projects, algorithm archive over here, npm run serve, and then we're going to go from there. Okay, once this is built, we'll open it up, and then, yeah, we'll take a look at it. I don't want to spend too much time on it, but I think spending a little bit of time is important. And then we'll take a look at the code, see what it does, see if we can fix it really quick, and then go from there. Good, good, good. Okay, let me open this up here. Move it up here. Okay, move it. Can I do this? Ho, ho. That almost worked. I forgot I had that keybind. All right, so let's go into localhost. There we go. And the Metropolis chapter. Here we go. And there was one particular thing I just wanted to check really quick, which is all the way down here. It should be the intro to the algorithm right here. I think that's actually fine. I think just saying it will be split up into a few parts. I think the main thing is that I don't really like having like a section and then a subsection immediately under it. So, I mean, we could just remove this entirely, which is fine. I don't know, I'm being super persnickety here, like who cares? Now let's dive into an actual algorithm for some example code. I might say something, well, it's just that there's a bunch of subsections here. So it's one of those things, right? Like it doesn't actually matter too much. Maybe we could just remove the heading entirely. Random walk in one direction, random walk with acceptance criterion. The initial setup. Let's see, what do we have here? How to iterate, example code. I think it's fine. It's fine. Okay, so let's take a look at the example code on my own branch and see what we got. So we're going to cd in contents, Metropolis. There we go. ls into, or cd into code, ls cd into Python, cd into Python, ls here. Okay, so we should just be able to run metropolis.py. So let's run Python, metropolis.py. Okay, so we have, what is NRM? Oh, it's root mean squared deviation or something like that. Let me take a look at the code, vi metropolis. Also, let's remove the output. And now let's do it one more time. Make sure it has some sort of output. ls here. So it does have an output.dat via output.dat. And I think this was the issue. This is unbinned data, and I think that's the problem. So when you look at the Metropolis algorithm in here, I don't have it up anymore. Yeah, so when you look at the Metropolis algorithm, what you want is a histogram, but this is not a histogram. And a lot of plotting software, I say a lot of plotting software, GNU Plot doesn't have an easy way to do histogramming. So the only criticism I have of the code right now, without even looking at the code, is that people cannot easily plot this output. Now I say people, I'm sure, I mean, like, you know, if you use probably a Python backend or something, whatever they use for Python is probably pretty easy. Probably the same is true for Julia. So maybe I just need to create a GNU plotting script for this. Okay. Plotting quick histogram. Sure, let's see what we got there. Okay. Here. So what do we have here? We have bin width is equal to 1.0. We have bin number is equal to x. And then we have rounded here. So we plot output.dat using rounded. So we round them. Then unity. What is unity? Oh, unity is equal to 1. Why do they have unity equal to 1? Why not just use 1? Can we just do, so it has to load histo.plot. So you can use the below script to plot a quick and dirty histogram of output data. There are 3 methods here. Only method 1 is uncommented. The only variable you need to set are the bin width and, wait, what do we have here? Copy load the script. So histo.plot. Okay, so in principle, we can just add this in, and we need to add this to the plotting script. Okay, so let me see what happens if we go here and just see if we can run this. So let's go here to vi plot.gp. Let's paste it in there. And let me see what happens if we run it. So now I'm just going to do vi plot.gp. Let's plot output.dat using rounded. Okay, so GNU plot.gp is just going to run. L is here. So we have output.dat plot.gp. So let's go here to plot.gp minus. Fine, it works. So we can just add a very simple histogramming like section to the plotting chapter. And so let me do control D, vi plot.gp. Let me modify this really quick. So we have bin width is here. So bin number x is going to be the floor of x over bin width. That seems fine. Rounded x. What is the license of this code? It is apparently unlicensed. So that's not good. So let me just go ahead and paste this here. And I'm going to put it into the chapter here. Or maybe I need... Did I already create an issue for this? I feel like I already created an issue for this. Let's go into issues. And histogram chapter for plotting chapter. Oh, that's it. This is literally what I wrote before. Okay, cool. So we just need to make sure that's done. And then I can say 935 here. Did I already link 935 to... Did I already link 935 to this PR before? Let's go to the pull request here. And let's go to... where are we? Metropolis here. And it was 935, I believe. So... I'm going here and just say, just leaving a quick comment here. Well, no, I've already reminded myself. So, okay, the big issue here is that we just can't plot this very easily. So overall, I think that's fine. Let's take a look at the source code one more time. I thought it was kind of fine. I don't remember having any complaints with it. So let's go into VI. What are we going to do? Metropolis.py. So here's what we're going to do. Tomorrow, and someone has to hold me to this, but tomorrow we're going to come back, and what I'm going to do for the Metropolis PR is I'm actually going to add to the plotting section a histogram subsection for the plotting chapter, which is necessary for the Metropolis algorithm. So I'll add that in tomorrow for my algorithm archive time. Outside of that, let's see, f is going to be normalized, f is equal to false. Sure, okay, that's fine. We have G, Metropolis step, Metropolis iterate, test Metropolis iterate, seems fine, name main. Yeah, overall this is fine. I'm not seeing anything wrong with the code. Of course, MRS has already looked at the code very extensively and has already done a lot of PRs here, or not a lot of PRs, but a lot of comments here. The only thing I have here is we have test Metropolis iterate. So we have bin width is equal to 0.25, bins is here. Okay, this should be fine. Okay, good. So we looked at it tomorrow for the algorithm archive portion. I need someone to remind me that we need to basically add in the histogram plotting chapter. I'm going to go ahead and put that on the stream chat on Discord so I remember. Okay, AAA for tomorrow will be histogram plotting subsection. Just reminding myself. Okay, just want to write it somewhere. Good. Okay, so I think that's going to be it for the algorithm archive work today. We have a PR merged. Great. Thank you so much, Amaris, for not only that algorithm archive PR, but also all the help with the Metropolis chapter. I think that chapter is mostly done. There's going to be some small edits to the text, but I think we can get that done like relatively soon, and I'm relatively happy with that. Then, once we get the Metropolis chapter in, I will also add in the histogram plotting, and then that's that chapter in. I'm relatively happy with that. Good. I'm going to hop into the 4D galaxy simulations now. We'll explain like what's going on with all of that, and we can talk about how it's going to go, everything, in just a second. Just give me 2 minutes break, and I'll be right back. Okay, good to go. Right, so before going any further, let me just go ahead and update people on what's going to happen. So, I mentioned at the start of the stream that I'm going to try to put out like relatively weekly videos, just talking about things that are happening on the Twitch stream, in particular like big things that are happening or like interesting things that have happened over the course of the past week. This is in some sense going to be like kind of like channel updates or like research updates or something like that. But you know what I realized was, when it comes to like showing people research, I don't like PopSci. And the reason I don't like PopSci is because people always treat it like it's just some sort of magic that people can't really directly interact with, right? And you know, part of what I realized was if I only show people the big, the big final piece of the research, like, oh, this is the amazing thing that we generated at the end. Here's a 4-dimensional galaxy, all this kind of stuff. Like, I'm running into the same fallacy that everyone else runs into, where like I am teaching research by only giving people the big milestones. And I think that's doing a disservice for the process. I think the entire process is interesting, even those little stumbling blocks you find along the way. So putting out, somewhat weekly videos, I think is really important to showing people what the actual process of research is like. So giving people a description of how I spent a week trying to convert, a single value that is 1.0 into an integer, like how that took a week, why it took a week. Talking about a lot of the bloopers that we got during the simulation yesterday, being like, oh, hey, this happened because of this happened because of this, all that kind of stuff. I think is super important. There's just a lot of like little things like that I think is like really I think it's worth explaining to people, right? Hey, LimeDie, how are you? That's not teaching research, that's teaching scientific results. Yeah, which is way less interesting. Right, exactly. And this is also, I think, part of the problem I have with like a lot of other content creators out there. And again, I've mentioned this before, but like part of the reason I don't particularly watch educational content on YouTube is because I always feel like a research paper is more engaging. And why is that? It's because research papers give you the actual process. You know that one result doesn't matter that much. You know it matters in the grand scope of other papers. And so I think that's what I need to show. I need to be like, hey, look, we're doing interesting stuff here. It's just that, sometimes you're going to spend weeks, maybe months, just working on a histogramming algorithm, and that's how it goes. But even that process is itself interesting. You just have to kind of not sell it in the right way, but you have to think about it in the right way. Like, this is serving this purpose. This is why we're doing this, and just kind of explaining how it all works together, I think is really important. And I don't think there's anyone on YouTube, well, there might be some people, but there's no big content creator out there that's really showing people like what it's like to do research on a day-to-day level. And sure, I acknowledge that the research I'm doing right now is not like groundbreaking or anything like that. I'm hoping that as we go throughout the year, the research becomes more and more important. But anyway, that's what I wanted to say. I think putting out more regular videos is kind of the way to go here. If only because putting out one video every 2 months when we actually have something important to say is not exactly a good, long-term strategy for YouTube. But also because I think we're selling the wrong result there. Like, the result shouldn't be, just learned that sleep is a new category on Twitch. Wait a minute. I know I'm rambling here, but let me check that out. Holy cow. Are you kidding me? Wait. So if I just go here and I type in sleep. Okay, come on. Is this actually... No, this must be a game, right? This must be a game. The main character, Jill, is often tormented by nightmares. Her friends ask her to look after their house while they are away. Wait a minute. This is supposed to be a game. But people are just sleeping on stream. That's kind of funny. So this guy's doing a 96-hour subathon. This person. How come they both have mustaches? Is this the same person? 24-hour subathon, sleeping back? Should we do a 24-hour subathon? Is this something we should do? Just sleep on stream? Is this what people are into? I mean, hey, I'll sleep on stream if that's what people want. I don't know. But I don't think that's what people want. I genuinely don't think people want to see me sleep on stream. That's really weird. Okay. Wooden Potatoes went live. Good for him. Okay. Anyway, back to the YouTube content. All I was going to say is that I think finding a way to just tell these other stories that are not as interesting, but also interesting in other ways, I think is really, really important. And I've been struggling with, whether I should make it so every single one of my videos is fundamentally new, so new that no one has ever seen it before, or if I should make each one of my videos more personality driven. And I think the truth is I kind of need to do a bit of both, where the big videos still have a purpose and will still go on my channel. But the smaller videos are still there because I think it's really important to show these smaller stories and try to explain why they're interesting, even if they don't initially seem that way. I don't know. I mean, maybe I'm just killing my channel, but my channel's already dead. So what's the worst that can happen, right? I just figured it out. People use that game as a category when they're sleeping, but it does refer to a game, right? And then Twitch will see that and probably add a just sleeping category. I think they should, subathons can use it. To be fair, you're right. I think subathons can use it. I find subathons super weird, by the way. For those of you guys who may not know, I certainly didn't know until very recently. There was a huge Twitch streamer called Ludwig, I think, who did a subathon recently where basically he made it so every time one of his, one of his community members subscribed, he would stay live for an extra, I think it was like 20 seconds or something ridiculous like that. And he got such a huge number of subscriptions that this actually kept him streaming for an entire month on Twitch. Could you imagine that? That's an insane amount of people subscribing to your channel. Like, I mean, I'm not going to sit here and say that that's a good thing to do because I don't want to do that. But man, it was a way to drum up support for his channel. Like, he became the most subscribed channel on Twitch, which is insane, Anyway, long story short, I I am not intending to do something like that. I think doing a 24-hour stream is quite difficult. Although recently I've been noticing my stream stamina has been increasing. Like doing a 6-hour stream now is fairly standard. It doesn't feel hard to do. And I think, if we keep doing these, then potentially longer streams could be on the table. But I think doing a 24-hour stream, for programming and science and tech content is maybe a bit much. I don't know. I really genuinely don't know who would watch me talk about science and tech for 24 hours. That would be kind of insane. Of course, people wouldn't be watching for the whole time, but I'm saying that, a long time ago, back in the glory days of this Twitch stream, there were a large number of people who were like, oh, you should do a 24-hour stream. I'm like, no, man, I'm not going to do a 24-hour stream. Why would I ever do a 24-hour stream? That sounds like insanity. 24-hour streams are difficult for everyone. 24 hours is too much for anything. Don't do 24 hours. It sucks. Anyway, all I was saying was that if I were to do that, I would probably also show people what I cook for lunch and all this kind of stuff as well. I actually feel like I'm a decent cook. I know maybe I'm not, but in general, if I go out to eat somewhere, I feel like the food that I cook at home is better. So anything, stuff like that. You probably need to switch to between chatting and science and tech. Oh, definitely. There's no way I could be in science and tech the whole time. I mean, unless I'm doing sleep apnea studies or something while I'm sleeping. We could do that. I could put an EEG or something on and try to sleep with that. It depends. You can just stream your life and it can be fine. Yeah, but no one wants to stream their life. I mean, I mentioned this before, even yesterday. I'm fundamentally different from when I'm streaming compared to when I'm just talking to people regularly, right? So it's one of those things where I could not keep my personality on the Twitch personality for that long. It's hard. There's a reason why I kept having to do these short streams and kind of burst my way into the longer streams, because it takes a while to just work your way up into feeling, keeping yourself on for so long. Again, one of the people I watch regularly on Twitch the other day said something along the lines of how Twitch streaming is an easy job because you're just playing video games all day. I'm like, really? I feel like Twitch streaming is I'm not saying it's hard, but I'm saying that it's about as hard as, for example, when I did work minimum wage at certain places, specifically when lifeguarding, which was one of the harder jobs, if you'd believe it, one of the harder jobs that I had to do when I was growing up. Just because you have to constantly be watching, you got the sun shining on you at all times, all this kind of stuff, it actually ends up being quite difficult. Especially when you've got 200 people in the pool. Anyway, the point is, compared to that job, streaming is more difficult than that. It is also, in my opinion, maybe because I'm doing science and tech content, more difficult than just doing normal research, right? But anyway, that's so, when people are like, oh, streaming's easy because all you're doing is playing video games all the time, I'm like, I don't know, it's not. I would not say it's easy, but maybe I'm just not the type of person that finds this type of thing easy, Slowly but surely you build yourself into it, you get more used to it, but it's not like I'm just sitting here and being like, oh, wow, this is super easy. I'm just going to stream my workday. I have to prep every stream to make sure that there's something I can do that day that ends up, taking a significant amount of time and will be somehow interesting to some extent. And I'm actually going to run into a wall tomorrow, because if we get through everything that we need to get through today, in principle, I'm not sure what we're doing tomorrow. I mean, look, I've read papers and papers and papers, but I'm not entirely sure exactly what direction to go in after today's stream. There's a bunch of different things to do, but I'm not sure. It depends if you just stream your life, but staying awake and doing a thing is really hard, right, for 24 hours. Be science pilled on everything for 24 hours. Science pilled is just being in the science and tech category. Being on high alert all the time is exhausting. I know because of my experience as a chess arbiter and also being autistic. Yeah. There's actually, anyway, I don't want to dive too deep into this and all that kind of stuff. I just want to say that, again, final word on YouTube. I'm going to try to put more regular content out, at least in the month of December, and see how it goes. This means that, I think the truth is, when people look at my content on YouTube, they don't, first of all, realize how long it takes for each video. And second of all, they don't realize, they don't see it as anything outside of a normal update video anyway. It seems like an update video to them, when for me it's took months of work to create this thing. Yeah, I should end the Rambleo stream, you're right. Anyway, point is, I'm done. I'm just going to put more regular content out on YouTube. I just want to let everyone know that I'm going to try it this month, see how it goes. with the primary focus of these videos for this month being to actually generate more hype around the Twitch stream, to just, really engage and be like, hey, this is where I do most of the live streaming work. This is where most of this stuff comes from. So if you're interested in like seeing the day-to-day experience, if you're interested in like just doing cool stuff together, this is where you do it. I was joking about not having to switch between just chatting and science and tech by talking about science and the science of everything, like cooking. Oh, that's fair. That's totally fair. But the problem there, oh gosh, I'm rambling again. Let me just go over here and let me go to Twitch. I can put this in Ramble Lows mode, but you guys need to see this. Okay, let me close that. Actually, I like to have my stream up in the background, so let me just go here to browse. Should still be, yep, perfect. Okay, so here's the big problem. A lot of science people who do science and tech on Twitch are actually in the just chatting category. Now, the problem with just chatting is the problem with pretty much all of Twitch, in that it's impossible to find good streams. Like you're looking at it, it's really, really difficult to find streams where like the people are engaging and interesting and all this kind of stuff, So it's like, it's hard. But what I do know is that a lot of the people, specifically in the, specifically in what category? The, specifically who were in the science and tech category, ended up going to where here? Ended up going to the just chatting category. What are you looking at? Oh, this one maybe? I don't know what that one is. Where are we going? More? I must have missed something. What am I looking for? This one? What am I looking for? This one? There's a bunch of weird ones. Down one? This one? Well, so now I don't know which one I'm looking for. I mean, you could just give me a link, I guess. But anyway, the point is, down one to the left. This one. Here. What? I don't understand. What's going on? Anyway, what I was down one more. Here? Where? Wait, Nihongo? Okay, I don't know which one I'm looking for. I'm so sorry. But anyway, here's the thing. Let me also go to browse again. Up here, there. That's a YouTuber I used to watch. Oh, interesting. I see. I didn't realize that. Cool. Cool. Does everyone else know that? Is a Chinese person watching her? Oh, okay. I thought it was like a super big coincidence. I was pretty excited about it. Okay, so let me just talk about this really quick. Right, so in my mind, when you go to the science and tech category on Twitch, which is, I don't even know anymore. I think I'm gonna have to go here and then there, and then we find it here. I would love it to be that when you go to the science and tech category, you find a high number of really interesting people doing really interesting things, right? That's what I want to see. I want to see people doing research on stream. I'm number 4. That's not bad. I'm just behind 24-hour stream and technical streams. I think that's fine. Anyway, my point is, I would love for people to go to the science and tech category and find like super interesting streams all the time, right? That would be amazing if we could see that. But you can currently kind of see that with the software and game development channel. But essentially, when science and tech came out, there were a bunch of people who chatted about science and tech. They talked about science and tech all the time. And they ended up moving to the just chatting category with the logic that they're still talking. They're just talking about science. And I feel like it's one of those things where you could be between the two categories, and most people ended up going to just chatting because there's more growth potential in just chatting than science and tech. Nowadays, because the software developers are now in their own category, the animal streams are now in their own category, I feel like we're at the stage where science and tech can flourish on Twitch, and I'm really looking forward to what it's going to be like in the next few months. If my gamble works out, which is a bit of a gamble, but if my channel ends up becoming more successful and we can start really funneling people into this stream, my hope is, and this isn't going to work out, but my hope is that we can slowly get more people doing research on science and tech on Twitch, so that when people go to Twitch, we can just say, hey, go to science and tech category. You're going to find something you like there. I can guarantee it. That's what I want to be able to say. I used to be able to say that with the programming category on Twitch. I used to be able to say, hey, go to the programming category. You'll definitely be able to find it. Anyway, what do we have here? It's just earthquake crap. To be honest, the earthquake crap is fine. Some people actually enjoy it. Someone from came on to stream yesterday who really enjoyed it and actually asked us to raid the channel afterwards. I was like, okay. So there's Vector the robot, right, with 30 people. Earthquakes, DDoS, robots, and 4D Galaxy simulations. Sometimes you get a female doing soldering really badly, but still has 100 plus people watching. Yeah, so I think the problem with the science and tech category right now is that people have kind of lost faith in the category as a whole, right? Because it used to be when you went there, you didn't really know what to find. And if you're going to go to Twitch, and you're going to go to a category that you don't know what to find, and you know you're not interested in gaming. I mean, it's the just chatting category. That's where you're going to go. You just go to the just chatting category. And the problem is, for me, like let's say I'm trying to recommend Twitch to anybody, literally any of my friends, right? What do? Right? So they might go to chess. In fact, chess is a game that a lot of people really like. They would probably click on just chatting. But in the top set of games or categories, frankly, this one and this one is interesting, but it gives people the impression that this particular website is specifically for games, which it is in some sense. But music, sports. So what I have to tell them is go to IRL here, and then you'll find a bunch of categories here that you could potentially find stuff that you like in, right? Hey, how are you? Nepo and Magnus are quickly heading towards the draw, by the way. I didn't even know what was going on. But my point is the following, right? Like, if you're asking for a normal person to watch a Twitch stream, the question is, where do they go on Twitch? And the answer is probably, if they just find their way on Twitch, they're going to find their way into the just chatting category. Because first of all, it's the number one category on Twitch. And second of all, it's not a gaming stream. And because of that, more people are probably going to go there because I don't know. I don't think people are super interested in gaming, in general. Like, obviously gamers are really invested in it, but in general, I just don't think it's true that people are overall interested in it. Is this actually Elon Musk? What? No way. Why are you guys here? You can watch Elon Musk. Anyway, point is, I don't know. It's just hard. It's hard to find streams. I'm rambling now. Point is, I'm upset with Twitch. I'm always upset with Twitch. I'm always upset with YouTube. I'm always upset with my life. Let's just get on with it. I think that's a scam stream. Could be. I don't know. My dad is super into Elon Musk, and I gotta be honest. I don't really know what to think about him. It's one of those things where it's like, I think he's doing some stuff that could potentially be cool, but I also feel like a lot of the stuff that Elon is doing should be publicly funded, not privately funded. And I feel like it's really, I don't know, I don't want to go into this conversation, but I feel like it's really unfortunate that, NASA, for example, is not being funded properly to do the stuff that Elon's doing, right? Like, it's like, why do we have to go private here? It's not like there's a huge, pushback between private and public here. Like, who cares? But anyway, I don't know. I get kind of a bit, I don't know. You think an alternative to Twitch, more focused on IRL research, would work and can compete? The answer is no. It's the same reason why every single YouTube competitor fails. It's just, sure, okay, Twitch in some sense can be a YouTube competitor, but even though Twitch is not, they just drawed. Really super interesting. You're saying it's a world championship. Anyway, 3 draws in a row. That is super interesting. Why are you here when you could be watching a Twitch or a chess stream? All right, give me a second. I'll be right back. Or I just need to move my stuff around. I'm not going to be right back. I'm still here. Okay. Sorry, oh man, I need to change position every now and again so my legs don't go stale. What was I going to say? I was going to say the following. There is a reason why no one can compete with YouTube. No matter what you do, no matter what approach you try, you can't compete with YouTube. And the reason is because YouTube is, first of all, where everybody is. And second of all, they have just way better server management than everywhere else. Twitch has the entirety of Amazon behind them. And so it's going to be hard to compete with that. Sure, okay. Twitch is, not really making money compared to YouTube or other places, but it's not going to die, right? And so trying to create a new live streaming platform is just, it's not something that you can make technically feasible easily, right? Not without like a huge amount of server space or something like that. So as much as I would love to see a Twitch, but more IRL, specifically research focused, it's not going to work because, one, there isn't the interest. 2, there isn't the, we don't have the server capacity. And 3, there aren't going to be enough scientists who are willing to do that type of thing, right? Which is why I think it's better just to stick with the science and tech category on Twitch and just say, hey, go here. This is where you're going to find interesting stuff. That's my personal opinion. Would be nice if instead of underground pod tunnels, you guys got better public transport instead. Oh yeah. All the jokes about like the boring company creating just another train or a subway, I totally agree with that. To be fair though, I am in Europe. And I just came from Japan, which has amazing public transportation, specifically through Tokyo and Kyoto and all these areas. So like honestly, I'm on the board. I'm on board with public transportation. Not a full draw championship, please. It's only the third match, and some of the draws were pretty exciting. They better be interesting. Anyway, we've been rambling about Twitch and YouTube and all this kind of stuff for a while. I am going to go ahead and move on to the actual research for today's stream because there's a lot of stuff to do. And I'm pretty excited with some of the research that we can do today. It's not going to be so researchy today. It's going to be more systems engineering today, but I'm still happy with it. The Teslas in tunnels is a fire disaster waiting to happen. I mean, to be fair, Teslas don't really the batteries sure are more flammable, but like it's very unlikely that your car is going to start on fire, right? In the case that it does set on fire, maybe it's a little bit more flammable, right? But like, I don't know. It's not. I think the whole like cars burning thing was kind of played up a bit too much because like when you saw what happened for most of the cars that like were set on fire and stuff, specifically the Teslas, it's like honestly they probably did better in that crash than most like combustion engine vehicles. Anyway, I'm gonna like kind of ramble about. I don't want to ramble about that because honestly we're moving into territories where I genuinely know nothing about this. They don't combust option, sure, but tunnel fires are really bad. That's also fair. That's totally fair. I accept that 100%. Again, I end up accidentally rambling about things that I don't know about, and I really want to make sure that we don't go into that territory here. Because like, there's a lot of things I'll just say on this stream, and I've been slowly realizing that over the course of time, I'm kind of becoming this curmudgeon. I think that's the word I'm looking for. I'm turning into this guy who like hates everything, and it's just because like the way I say it in stream makes it seem like I hate everything, when in fact I'm actually quite positive about it, you know? Like, if you ask me about like what I think about, you know, YouTube in general, I'm like, it's great. You know, I genuinely love, I love the fact that so many people are doing really good educational content on YouTube. It's just when you compare my channel to other channels, then I get defensive. And then it makes it sound like I hate everybody. And it's like, well, okay, what I acknowledge is that YouTube's not for me. Twitch, I actually really like. And, you know, this is the kind of stuff that I just need to be clearer about in the future. I need to be like, hey, look, what I need to do is be less like, oh, I hate this thing, and more like, hey, that thing's great. If you like it, great, is what I need to do, if that makes sense. You know, there's two different ways to go about it. It's a problem for all tunnels. However, if they don't have fire-safe tunnels, that's going to be a problem. I would like to say I'd be surprised if they didn't have fire-safe tunnels, but now I'm actually going to be surprised if they do have fire-safe tunnels. I really don't know. Anyway, let's go ahead and move on to the bulk of today's stream, which is going to be the four-dimensional Galaxy Simulator. Whoa. Yeah, I'm excited. Amazing. Anyway, so what's going on here? If you look at these visualizations over here in the upper left-hand corner, let's go ahead and full screen this. You're seeing what's called an n-body simulation. The idea is that every single particle looks at every other particle in the simulation and asks itself, hey, how exactly am I going to move? Am I going to move closer, or am I going to move further away from all these particles? The way this works is that every single particle exhibits some sort of gravitational potential. So it's all trying to attract all of the particles together. That's what it's trying to do, which is why you see, for example, this guy right here move back into the center here. We have right now an n-dimensional particle simulator. That is to say, we can simulate up to n dimensions where n could be anything. Now, yesterday, and the day before that, and technically the day before that, we were working on optimizing this specifically for the GPU, and we run into a bunch of different issues. The first big issue is that this is an n-squared complex system. That is to say that every single particle needs to look at every other particle. So each particle has n operations, and you have n particles, so it's an n-squared operation. The most difficult part of this simulation, after doing a lot of profiling results yesterday, ended up being exactly what you might expect, which is the determination of the acceleration on each individual particle. Because what you're doing here is you're going through all the different accelerations coming from each of the particles and adding them all together into one big unit, which means you have to do a type of parallel summation. Now, we've got two different ways to do the parallelization here. 1 second, let me unfull screen that guy, let it play. So we've got two different ways to do the parallelization here across the GPU. The first is basically to say, okay, we're going to have every thread, we're going to have every thread do all the computation. Okay. The other thing is to make it so the other thing we could do is have two separate operations. One operation where we find the acceleration on a single particle. So maybe a loop through the particles, right? And then the next step is going to be find acceleration vector. This is to say the component, the acceleration component for each individual point. So you'd have sorry about that, I hit the microphone. You'd have a list of n elements, and in this list of n elements, you have the acceleration due to particle 1, the acceleration due to particle 2, the acceleration due to particle 3, so on and so forth. And then 3, do a parallel sum. Okay, so here's the thing. Number 1 here is the one that we currently have in code. I am pretty convinced this is a slower way to do it. However, we're trying to optimize this as fast as we can so we can benchmark it against this guy. It's not obvious to me which one's going to be faster, because this one here it basically has a single kernel, so one kernel, whereas this will have n kernels, actually n times 3 kernels, 3 n kernels, of which this parallel sum is not particularly well optimized anyway. So we end up running into this situation, 2n kernels, I got that wrong. 2n kernels, because the first one's just a loop. So this is going to be 2n kernels. Okay, which means you have an additional kernel launch every time you have to run this. So you have 2 additional kernel launches. Now, kernel launches take a little bit of time, depending on how they're implemented. So we're running into a situation where we have one big beefy kernel, or 2n smaller kernels, which can more effectively use the threads. I don't know. I think my naive intuition is that this one's actually going to be faster. But this one is what we have right now. So what I tried doing yesterday was I tried to optimize this code by using shared memory resources. So what this means is using additional memory resources on the GPU that allows threads to have faster access to the data. And when I did this, we actually ran into a problem where the code ran 3 times slower. As weird as that is, 3 times slower after doing things that should have optimized it. I think I found the big problem with it, so we're going to try to fix that and see if that speeds our code up again to make it so it's at least on par with the code we had 2 days ago. And so that's what we're going to work on today. It's a lot of systems engineering, a lot of GPU work. I do recognize that, again, people are here for the 4D Galaxy simulation, and we go from there. If they don't have fire-safe tunnels, that's going to be a problem. Right. I like your OS setup, by the way. Thank you so much. Really appreciate that. If you're interested in the OS setup, let me go here to stream. Let me go to off topic here, and let me give you a link. I don't know if that link will work or not. Let me try it again. Here, off topic, create invite, copy, paste there. Paste it there. No, I didn't do Barnes Hut already. I'm trying to optimize the n-body simulation so that we can get a proper benchmark against the Barnes Hut simulation when we do it. So for those who are asking what the Barnes Hut simulation is, let's go here. So we showed that we have this n-body interaction. So we have all these particles in space, right? And the idea is that all of these particles are just floating around trying to figure out what their velocities will be, their accelerations will be at any time step. Now, you could imagine, again, like we just said, this is an n-body interaction. So all of this particle has to look at every other particle in the simulation. But in principle, these particles are far enough away that you could kind of treat this as one big massive blob of particles instead of a whole bunch of smaller particles, which will cut down the number of interactions, the number of calculations you need to do. The Barnes-Hut algorithm, I'm not going to go into the full details here, basically allows you to cut the particles spatially into little boxes. And then it basically says, okay, we're going to put all these particles into a box, to put all those particles into a bigger box, such that you can basically approximate the result of the simulation. We will do Barnes-Hut. It might not be until tomorrow, but we're going to get this done. I'm not smart, but smart with this stuff, but would it be 2 threads given the small kernels instead of 1 thread? No, so this has to be launched. There's an @synchronized statement between the two here, you could imagine. But it's not really just an at sync. You have to let the whole kernel die. The reason this is this way is that we can't really do concurrency here super well. By the way, Dario Cooper, thank you so much for following. Really appreciate it. Right, so it's going to have to use the advantage to this one. The reason this one's advantageous is because you can use the full GPU in an optimized way for all the calculation. That's why I think this one might be better. So if we end up doing this thing where we use like 2 threads to like smaller kernels and stuff, I don't think that's going to be super optimal. But this is something that we can look at later. Right now, we're going to focus on optimizing the n-body interactions. So just to clear things up, the Barnes-Hut algorithm is something that we will be implementing. Barnes-Hut is something we will be implementing. It will probably be either tomorrow or the next day. The reason I'm waiting on it is because I do want to get a proper benchmark between it and the n-body simulations. And to do that, we want the fastest possible n-body simulation. I don't want to be like, oh, wow, we're 10 times faster than naive, n-body simulations if my code for the n-body simulation is just garbage, if I could speed up the n-body simulation by a factor of 10 or something by doing this thing instead of that thing, first of all, we learn a lot of GPU engineering tricks, but second of all, it helps us out in the long run. It means that we get better scientific results by being more accurate about these small things. This is again one of those reasons why I decided to change the YouTube content to be more how do I put it? More like episodic in nature, less like big picture in nature, because I realized if I'm only shooting for big videos, it's going to kind of entice me. It's going to lead me to want to be less rigorous about the scientific results, and I don't think that's fair. Are you going to be parallelizing Barnes-Hut as well? Yes, so this will be parallel. Definitely going to be parallel. By the way, I don't know why, but this is my sign for parallel. I've got all these like weird notational like signs that I use a lot, and I don't know if I've explained them. This is parallel. This is a measurement. So if I just say I want to measure something, I use this for measurement. I've got a bunch of other ones as well that I just kind of draw, and I'm like, this is what I don't know why, but just it's kind of like sept its way into my writing all the time. So I'm like, this is in parallel, or this is measuring this, this type of thing. I don't know. I use them all the time. So if I accidentally show any of those symbols on stream, that's what they mean. It's just, I don't know. I just end up randomly doing that. All right, so we're gonna CD into projects. Galilee. Okay, Galilee here, and we're gonna go over here. CD projects Galilee. Okay, let's go into vi source and forces.jl. Right. So basically yesterday, we realized that the code that we wrote was like 3 times slower than the code we had the day before. The big difference between the code we had the day before and the code we had yesterday is that the code we made yesterday makes use of these shared memory resources, i.e. the local memory here, float64. Now, what I failed to realize is that even though we are updating, the local memory, even though we're updating the shared memory fairly regularly, like even though it is fast to update this process, that's what I mean to say, even though it's fast to update the shared memory resource, we need to consider each of the reads that we're doing here. So what's actually happening here is we create this temporary set of positions here, which is going to be the position of the particle that we're looking at. So we have the particle that we're looking at, and then we have all the other particles in the simulation that we're summing with. So we're focused on this one particle, and we're looking at all these other particles in the simulation, right? And so the idea is we have a temp position for that, and we have a temp acceleration, which we're just going to constantly add to, right? So because we have one access to global memory here, and we have another access to global memory here. But what I failed to realize is that I wanted to create a second set of temporary positions. And what I wanted to do was use this additional set of temporary positions because it's relatively fast to access shared memory, but relatively slow to access global memory. So I thought, okay, well, let's just copy onto the shared memory resource. But what this means is we're actually going to do a global memory check here, and then in this force law, we're going to have a local memory check. And so essentially, this temp position 2 is completely useless because all this is doing, it's not avoiding any global memory checks. We essentially have to do 2 or 3 times the work. So this is what we need to focus on, what we need to fix. Fabus, thank you so much for the bit. And also, I need Java. Thank you so much for following. Unfortunately, we are not going to be doing Java probably ever on this channel. It might come up, but probably not. So what I'm going to do first is I'm going to remove this temp position 2 entirely. And I'm basically going to modify all of the force laws so that they basically will read in the set of positions here instead. So we'll have a temporary position, which is going to be in shared memory, and temporary acceleration. Let me think, does that actually make sense? So we're going to have a global memory look here and temp position here. I also thought maybe another good thing to do would be to change the axes. So the Y and the X axes are flipped so that we can make use of memory coalescence. Because what I realized was in pretty much all of these operations, we're going to be we're looking across the X, Y, and Z axis here, which means we're doing lookups along like X, Y, Z. And for that, we probably, but the data is allocated like particle, particle, particle instead of X, Y, Z. So yeah, I don't know. I need to think about how we actually want to do this, but I think maybe flipping the axes would be good here. It's only going to be used for Java PRs in the algorithm archive. That's probably fair. I have 20 bits left. I'm going to give them to you. Oh, thank you so much. Really appreciate it. Thank you so much for the 20 bits. I really appreciate it. Okay, so let's keep going then. We're going to remove temp position 2. I'm going to change this so that these guys just read in positions here. Positions. And then we also probably want to read in J as well here. So I'm going to check this out with gravity and see if this speeds anything up. I probably want to do a git stash. Yeah. Okay, let's do this then. We're going to do J here. And then we want, whereas position 2 is going to be, this is going to be mess, isn't it? It's just going to be positions 2 here, there, and do we have any other position 2 here? J, J, and J. In principle, what I should do... this is just messy. Yeah, okay. I don't actually know the best way to do this. Because I can't create an auxiliary array because we're on the GPU. So what I might do is I might just run this really quick. And see if this fixes anything. So we're going to run Julia -- project. And we're going to see what happens. So we're going to be using CUDA and Galilee. We're going to give it a go and see, how fast it is. I've got a feeling it's going to be kind of slow. But that's okay. Looking at the timings yesterday, essentially we had like a 60-second run for something that should have been 20 seconds. So if this speeds it up to be like 40 seconds, then, we can kind of go from there. So we're going to run Galilee.run. We want to run it with just gravity. This should work. And let's just run that. Oh, that might not run because I have an extra comma out there at the end. But that's okay. So again, we're running this on the GPU. We are using kernel abstractions, which allows for us to write a single piece of code that can execute on the CPU and GPU, CPU or GPU, technically both as well, but usually you don't want to run the same code on both. Okay, so this definitely broke. Let's see how it broke. Okay, Control D. Let's go over here and let's mess around with it. VI source, forces. The big problem with kernel abstractions is that the error messages are just, they're bad. What I might want to do is just run it on the CPU again really quick. And running on the CPU should probably give me a better explanation of what's happening. So reading in J, and then over here we're also reading in J. Is this because... I don't know why this is. So we have temp acceleration, we have positions. Should be fine. Okay, let's go here. Let's try running it on the CPU. Julia. Control C. Control D. Julia -- project. Oh, and again, guys, if you have any comments, questions, concerns, anything like that, feel free to let me know. I'll totally address it as soon as I see it in chat. Hadlo, thank you so much for following. Really appreciate it. All right, we're going to be using CUDA and Galilee and just give this guy a go. Again, I'm going to run it on the CPU because the GPU did not seem to work. And sometimes you get slightly better error messages on the CPU than you do the GPU, specifically single core. So let's go here, and we're going to modify it so it runs on a simple array instead of a coup array. And let's remove this, and let's run it. If it runs, I'm going to try it again for a coup array. It does not run. It gives us an issue, and the issue is going to be... let's see, wait. Bounds error, attempt to access 256 by 2. Float 64 at index 2.3. Interesting. I saw your YouTube channel, really liked it, especially the tree traversal explanation using cards. Yeah, I thought that was an intuitive way to do it. I'm not going to sit here and say that all the videos are super good, because there's a lot of videos in there that I could have done better with, like, honestly, look, every time you look back at your content, like, same thing with cooking, like, anytime you make a dish or something like that, you're going to look at it and you're going to be like, oh man, like, there's all these things you could have done better. But overall, I think the channel is coming along nicely, and it's just a matter of, like, really cultivating it and, like, building it into something that I think people will really appreciate, you know? I prefer to do shorter videos to longer videos, all these different things, but I'm glad you're liking the YouTube content. Like I said earlier in stream, I'm really going to do what I can to put out more regular content this month and just see how that goes. By this month, I mean December. So I'm going to try to publish a video every week, and I think I'm going to try to make like Sunday my my like publish day or something like that. Okay, so bounds error attempt to access 256 by 2 at index 2.3. All right. How did that happen? 1 second. I think the issue here is that, why is it 256 by 2? Because we have 256 particles and it's trying to access it at element 3. So that must mean up here, we're running with the wrong local index. Position 2, 256 by 2. Wait, what? How is this happening? At index 2, 3, which means, what? Let's go over here. We're running a two-dimensional simulation. Why are we even going to index 3? Also, what's trying to access? Are we dumb? Is this going to give us a line number? Does this give us a line number? I'd love a line number. Over to forces line 41. Here. LIDK, position JK. So J here is going to be, no, K must be the problem. Wait, what? Let me output K. No, there's no way. Position 1, 2 should only go up to 2. What's going on here? Okay, let me just go here and do at print size of position 1, 2. And then we're going to put in a new line. Write this, go over here, using CUDA Gallery. I don't know if that's going to work. No, it didn't work. All right, so we're going to have to refresh everything. Julia double dash project, using CUDA Gallery, and let's try it one more time. See where it goes. Oh, I don't know. Like, this is going to be another one of those days where it's going to feel like we're tearing our hair out. It's going to be a little bit frustrating, which is fine. You know, sometimes days are like that, and that's just what it is, you know? Okay, let's go up here. It output 4. Why is it of size 4? I don't understand. Position 1, 2 should be the number of dimensions. So the way I have this set up is the position should be the number of elements and then the number of dimensions. So we're running a two-dimensional simulation. So it doesn't make sense to me that positions of 1, 2 is going to be... Oh, wait. I think I understand now. This should be... I see. Okay, I understand what's happening now. I totally understand what's happening now. Right. This also makes a lot of sense. Okay. I got it. We need to read in N is what we need to read in. For this, yeah, we need to read in N as well. Let me go back to the previous code that we had. Actually, what is the best way to do this? I could get stash. It's weird though. So what's happening here is we have positions LIDK, and then we have an access here, an access here. I'm still convinced the global memory or the shared memory access here is best. Git stash. Okay, let's go into forces.jl. Here we are. And let's go here to function repulsive, and let's just read in N to all of these guys, N to all of these guys, and just go to N. There. Here. And let's go down here and also read it into this guy, force law. Perfect. Now, what we're going to do is make it so all of these loops only go up to N. So let's go ahead and remove these. DT, D dollar sign is what I want. D dollar sign there, here, there, and up one more. There, and there. Now let's do N, 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 oh, N, oop, N, and N. And let's run this one more time. So I'm going to do Julia double dash project. Sure. using CUDA and Galilee, and let's see if we can get that runtime down. I'm just surprised it took 60 seconds. It's insane. Anyway, we'll try to figure it out. So now we want to run just one single Galilee run, just to make sure we're getting something working. Change this to cuArray. In principle, this should work just fine. So the issue we were having before was that the shared memory resource has to be a constant size, and that constant size was set to 4, so we could do up to 4-dimensional simulations. Because of that, we ran into an issue where that constant size was the size of position 1, so we were doing basically like additional computation when we didn't need to do that. So what I feel, and I'm not sure if this is true, but what I feel is that maybe we can get around this by there has to be some sort of shared memory hackery that we can do to get around this, is what I'm trying to say. So let me go over here. We're going to run CUDA at profile. Is there like an at time? Can I just use at time here for Galilee.run 2048? Yeah, this is a 1-dimensional simulation though. Let me try running this in 2 dimensions. Here, and let's see if this saves any time. Before it took like 60 seconds to do this. So let's just see how long it takes. So you guys probably have a minute to just go ahead and talk about whatever you want to talk about in chat. If you guys have any questions, comments, concerns, anything like that, just feel free to let me know. Man, I just realized, so I've been slowly sinking throughout the stream today. I was way higher when I started the stream, and now I'm like slowly going down further and further. And it's because these cushions I'm sitting on are just kind of sinking a little bit. I think it's probably still kind of in frame. Yeah, I guess it's fine. 1 second, move down just a hair. I don't know if that did anything. Anyway, we're still waiting for the code to run. This is a typical Simuleos fashion or Leos Labs fashion, just waiting for code to finish. Let's just see what happens. After this is done, I'm not sure the best thing to do. I have some code that's stashed away, but it's actually very easy to do. 54 seconds. With 4.75 million allocations, garbage collection time. Let me try CUDA.atTime instead of just at time. What's your opinion on Python? Python's nice. I mean, I don't use it for very much, but you know, it's nice. The only thing I've used Python for recently was a terminal video game like that I did a few years ago. But ultimately, I don't use Python for scientific computing because I just don't trust it to be fast. It's not that it's slow, because I know with like Cython and with a bunch of other things, you can make it fast. I just don't trust it to be fast. And I don't know what that means. I think it means that I am kind of afraid of running into something with Python that ends up taking a lot longer, just because it's Python. The thing about high performance computing is that you always care about, like, you know, the speed of little things. Like, I'm performance testing an n-body simulation that we're not actually going to use because we care about like weird, stupid benchmarks and stuff. This is interesting to me. Oh, we're running array. Let me run this to cuArray. Are you kidding me? Oh, shoot. I think I found out why it was so slow. I was using... Oh, I'm an idiot. Oh, no. I'm a complete idiot. Oh, no. It's actually phenomenally faster. It's actually way faster. I was running it on an array, not a cuArray. So when I was running the at times, I was timing the wrong thing. Thank goodness my intuition is not wrong. Holy crap. Like the whole night last night, I was sitting there, I was like, why? I don't understand. I don't understand how using shared memory here was slower. Like I was genuinely like my mind was blown, literally blown. I was like, how? How is it slower? Oh my gosh. Okay, give me a second. Let me just, okay, give me a second. Good. The change we made was good. Let's commit that change. And then I'm going to benchmark it versus the code from 2 days ago and check to see how much faster it is, because I think it's phenomenally faster. Oh, okay. I can simulate the exact same number of particles I could before. It's just now it's faster, you know? This is how progress is made. One typo at a time. Oh my gosh, I just can't. Like I need a moment. Like I really need a moment to just like calm down. Like I was so worried about this yesterday. I don't think you understand. I basically didn't sleep last night. Like I went upstairs and I was just a zombie after stream. I was like, I just don't understand. Like my wife was hearing me stream and she was hearing how excited I was and how like, you know, everything. And then like I come upstairs and I'm just dead. You know, for a number of different reasons. I got a message on Facebook that also, or Messenger or whatever, that made me unhappy. But then I just like sat there and I was just thinking, I was like, how? How is this possible? I don't understand. And I spent the whole night just like not saying anything. And I felt so bad because like my wife had just come back from a conference. You know, we hadn't seen each other in a few days. And I was like, I just can't. The only thing on my mind was how shared memory was slower. And I couldn't understand how that could possibly be the case. And here we are with a single typo. Oh, gosh. Oh, my gosh. Anyway, let me get status dot get add source forces. The anger of finding solving a dumb bug is very relatable. Yeah, it is what it is. Like I know everyone's done this before, but it's just like, oh my gosh, it's just how deep the rabbit hole goes here. Git commit dash m allowing code removing unnecessary computation for n less than 4 is what I'll say. All right, git push origin development. Oh gosh, give me a second. And this is research, ladies and gentlemen, and others. Oh gosh. Okay, let's keep going. So I'm gonna git checkout git log really quick, and let me check out a previous branch, which is this one. And we're just going to check it out and see how much faster we are. So that one took 7 seconds. Let me double check. It took 7.38 seconds. So now we're going to do git checkout. This guy. Perfect. Now we're going to do Julia double dash project. All right, now we're going to do using CUDA and Galilee. Oh my gosh, I can't believe that. There were a couple things that happened yesterday that I was like, I can't believe that happened yesterday. Like so many bloopers happened yesterday. Like I can show them to you in just a second. In fact, maybe I should show them to you because they're quite funny. But my gosh, I had so many typos yesterday. I mentioned this during stream. I was quite tired yesterday. So my brain was not entirely there. And you should never code when your brain isn't there. But anyway, let's run this guy with the Coo-Ray, and we're going to run it. And then we're going to do the benchmark. And I'm going to double check the CUDA at time command to make sure that we weren't doing file IO. I don't think we were, but I need to double check. But I think we're good. I think the code is actually running 3 times faster with the shared memory usage, which makes sense to me. Anything else just would not have made sense to me. So now we're going to do CUDA at time, this exact command. Let's run it. And then we have to double check that the code is running for the 4D force law and the repulsive force law, just to make sure it's working correctly, and we should be good to go. That took 8 seconds. So, okay, we're not that much faster, but we're a little bit faster, just a little bit faster, and that's fine. 22 and 56.0.01.100 doesn't look like a correct IP address. Where is that? Is that on my screen? Where's that from? Oh. You are correct. That's not a correct IP address. Okay. What I want to try is one more thing. I want to switch all of the axes so that the primary axis is now across the dimensions instead of being across the particle number. Yeah, I want to do that. I'm not sure if this is actually going to fix anything, but I want to try that. Git checkout. Git checkout development. I'm going to do something really quick. Where is it? 1 second. I don't like that song. All right, so the next thing I want to do is try switching axes. The reason I want to switch axes is because we are constantly grabbing elements along X, Y, and Z. And it's nice to grab a coalesced bit of data. Right now we are not, by coalesced I mean data right next to each other. So if we go into, where are we, forces.jl, you see here, like, we're constantly grabbing the X, Y, and Z axes. And I'm trying to think of a way in which we can split this kernel up so that it is, There's probably a way to split this kernel up so that we can make it two-dimensional. Let me think about that. So right now we're only indexing linearly, but we could make it so we index across the x, y, and z dimensions as well. The only problem with this is that for the force law calculation in here, we specifically have a sum over x, y, and z. So because of that, we're running into a situation where we have this k1 through n, and also it's not clear to me because if we split it up along that way, then we, it's not clear to me that's actually going to be better. It could be weirdly formatted IPv6 address. I gotta be honest, I know nothing about any of that stuff. I don't even know what that means. I genuinely should, but I don't. I just kind of nod my head when people talk about that kind of stuff. There's a lot of things like that I just kind of nod my head about. I'm like, yeah, that makes sense. Yeah. But I genuinely know nothing about it. Okay. So let me try switching the axes. Let me try switching the axes here. I'm not convinced it's going to speed anything up, but it might. Specifically because we've got this for loop in here, and it's kind of bothering me. Congrats on fixing the code. I also just realized what's wrong with your 4D R3 term. Wait, what's wrong with the 4D R3 term? I think you mentioned this. It's guaranteed to be. It's not guaranteed to be positive. Yeah, feel free to talk about it. What's wrong? Why is it guaranteed not to be positive, or why is it not guaranteed to be positive? Wait, it's not guaranteed to be positive, but it should always be negative. You should take the absolute of it. Oh, that is correct. That is definitely correct. For R3, that is wrong. Okay, yes, let's go ahead and fix that right now. So we're going to grab abs of this guy. You are definitely correct. Okay, let's try this again with the R3 calculation. Let's just actually run this code a couple times and check the R2. So we're going to check gravity. We're going to check 4D gravity, and we're going to check repulsive forces just to make sure they're all working. Let's go over here. Let's remove accelerations and then check .dat. Let's go over here, and we're going to do, actually, we'll just do it over here. Julia, -- project. Okay, and now we're going to run using CUDA and Galilee. Okay, so now my naive question here. Is it worth switching the axes? I'm going to try it. I want to try it. I want to see if we actually get any performance difference at all from switching the axes. I don't think we will, but there's a small chance we get a big speed up. So it's worth looking at. So now we're going to do Galilee.run. This is going to be for, let's do a force law. It's going to be equal to, let's do repulsive first and check to make sure that's working. Oh, that's not going to work. You should break. Please break. CD into aux. I accidentally typed in the wrong thing. Give it a second, and then we'll check it again. And again, guys, if you have any comments, questions, concerns, ideas, not even about the gravity simulation, but about whatever, feel free to ask. Let's go here, and let's put a comma in there, because that's actually what I needed. Perfect. There. Oh, I screwed up. What did I do wrong? Repulsive, not defined. What did I call it? Repulsive. Repulsive. Oh, it's Galilee.repulsive. There we go. Got it. What physical process does 40R cubed force law correspond to? It corresponds to the fact that journal new page, whatever. So you have a force is equal to GMM over R squared. This is going to be your traditional force law for like one particle versus another for the force of gravity. But in 3D, essentially in order to generate this, it's been a long time. What is the actual, I don't remember what the actual integral is, but essentially we have to integrate over the z dimension as well, or w dimension as well. And that integral over the w dimension from like 0 to infinity or something over the w dimension, probably negative infinity to positive infinity, and the w dimension will mean that we have to do an additional, basically you need to integrate this, which is going to be whatever it was before. So g is going to turn into GMM over R cubed, 6R cubed is what it's going to turn into. I don't exactly remember the full derivation here. It's been a long time, but the Force law basically changes in 4D, so it's over R cubed instead. So what Shadipto just said was that this fix basically allows us to like ensure that the result is negative, or the resulting denominator is always positive, which is good. Is the 4 plus 1D? Yes, it's a 4D gravity simulation. We're not doing space-time. It's an n-body simulation. Do you know anything about drone physics? I don't know much about drone physics at all. I don't even know what that means exactly, outside of like PID controls and stuff like this, which could be used for drones. I know nothing else outside of that. But feel free to talk about it, because I love learning more about this type of stuff. So yeah, it is a 4-dimensional simulation with time. We're not doing space-time. It's an n-body gravity simulation, right? So I think a lot of people, when they come in, they think 4D, they think I mean time as the 4th dimension. I really don't know why people think that. I guess it's just because people think cosmology and they think space-time. What's the motivation for thinking about 4 plus 1D classical gravity? Well, right. So there isn't the motivation here. There's a bunch of little things that I'm kind of motivated in for, but the big motivation here is just to figure out how the Barnes-Hut algorithm scales with extra dimensions. That's what I'm actually interested in. Finding a way to use this algorithm that's used all the time for n-body simulations and do it for higher dimensions, do it for n dimensions, right? How exactly do we do that scaling? That's what I'm interested in. I'm also interested in using the scaling laws, or using the techniques that we've learned from n-body simulations in other fields, like computer graphics and stuff like that. The physical reason for this, to be fair, isn't much. It's kind of cool to do a 4D galaxy simulation. Why not? But there's also the additional bit here that I'm just genuinely curious. If you do a 4-dimensional galaxy simulation, can you get 2 double rotating galaxies, or one galaxy that's a double rotating disk? Because in principle, in 4D, you can rotate along the X, Y, and ZW plane at the same time. So is this something you could feasibly get? I don't know. Maybe not. I have no idea. So this is why I'm kind of curious about that, as just a neat little like thing to kind of tie the research together with. That's kind of what I'm looking at. It's for the simulation of drones, so you can configure the needed PIDs. Right. So outside of that, I genuinely don't know anything about drones. Outside, they probably use PID. That's it. How to not kill your Krillin. Thank you so much for following a few minutes ago. Really appreciate it. Okay. Let's take a look at this 2D result just to make sure it's working correctly. So we're going to do GNU plot and just plot everything. Again, there's much faster ways to do this plot. I'm just doing it in GNU plot just because that's how I feel like doing it. And we're just going to see how it goes. Let's see, what time is it? It's currently about 5 o'clock. Really, it's 5 o'clock. Crazy. That means I've got about 3 hours left in stream, which is not as much time as I'd like, but we'll see how it goes. So if the simulation is correct, done correctly, then all the particles should just fly away. We should see them all just fly right away. And they do. Perfect. That's exactly what I wanted to see. Now, I am noticing something weird. This frame and that frame are entirely different. And I'm not entirely sure why that's the case. I don't know if this is a GNU plot issue or what, but this seems like the initial frame of the simulation. I don't know what's going on outside of that. It must be like a 1-based indexing or something. I must be off somehow. Okay, so what I'm going to do next is I'm going to run this in 4D now with the new Force law. So it's going to be gravity 4D. Gravity 4D. And we're going to do Critic Sense 2 DIMS 4. And this will project it down to 3D. And let's give it a go and see what it looks like. Again, so what we're doing here is a 4-dimensional simulation using the new Force law that Shadipto just fixed for us. Thank you for that. And then we're going to see what happens. So we're going to run GNU plot here, get those plots out, and we're projecting it down to 3D. Hopefully, it looks better than the plot that you see up there in the upper left-hand corner. That's currently the 4D plot. It's not really doing anything. I suspect it's going to be the same, or it's going to look very similar, and I'm not going to be able to tell the difference, really. Let's see. Maybe you're not generating the first image and we're using the old one. Right, I think that might be what's happening. Let's just take a look at Mirage here. Yeah, so clearly that's what I'm doing. Oh, I plotted it in a 2D anyway. I'm dumb. So we want to do GNU plot. Just plot, I think will work. Yeah, let's just do plot. Huh? Oh, I'm stupid. I need to remove the data files. All right, let's try running it again, and let's do it one more time. See what happens. And then once that's done, we can do this guy, plot.gp, plotting it in 3D, and we're going to see what happens. I'm not convinced this is going to be any different, but who knows? I've been wrong before many times within the past 6 hours or past like a few streams. I've been wrong a lot. That's just how it goes. Like, again, there was a time back during the PhD that my physical intuition was actually pretty good. Now it is definitely not good at all. So let's run Mirage here. Okay, so here's our set, and let's see what happens. They're all coming together, and oh, okay, that fixed it. Shadipto was right. Good, wonderful. This means we can probably get our galaxies that we're looking for. That's kind of surprising. I mean, look, they're not going to be like, it's not going to be a stable galaxy, right? But we should at least be able to get like angles of rotation, like, or rotational like disks is what we're looking for. It's not going to be like particularly good looking, but also there's something weird going on here and I don't understand it. Let me go here. Let me turn the video into an actual video. So let's do Mogrify and let me watch it because something weird is going on there that I'm not entirely happy with. Have you thought about using color for the fourth dimension for the points? So this is a projection from fourth dimension. Yeah, so the issue with color there is that if you do 3 spatial dimensions and then color, I think it's just very difficult. I don't know. I don't know if that's the best visual. Anyway, we thought about it. I'm not sure what the best actual solution is here. So let me do /create video. Yes. And let's see what happens. So we're going to get this video, and now we're going to do mpv temp test.mp4. Okay, so we have this guy coming in. Now, here's the thing that's weird to me. Let me go to full screen this guy. So again, this is a 4-dimensional simulation with the new force law. Just go back home. Stop it. Where's the home button? Okay, let's just press that. There we go. Full screen that guy. Here's the simulation. Starts off here. Next frame is this one. Perfect. Moves forward, clashes together. Perfect. Here's where things get funky to me. They're moving around like this. This is fine. Again, we're projecting down to 3D, so I'm expecting weird things to happen. But the whole cluster seems to be moving a little bit to the left, does it not? It looks like the whole thing is just moving. Am I wrong about that? Let me try doing this again, except just 2D with the R-cubed force law. But it looks like it's drifting, doesn't it? I'm not going crazy, right? Yeah, the center's like here. This is like, it's just running away. This could be, let me run it one more time. With a different number of points. The reason I want to do this is because if I run it again with a different number of points, what I think might be happening here is that the clusters mean more for an R-cubed force law. Which means that if there was a large, weird distribution of points over here, it could mean that all the points are kind of going towards that. Let's see, what do we have here? Have you thought about using color? It's even rotating. Is the initial data set to 0 momentum? Could be some points flew off to the right, carrying some momentum away. Yeah, so they're all starting off with 0 velocity. Let's look at a larger box. We can do that as well. It's not necessarily illogical if your cluster is unbalanced in the start. Right. That's what I was thinking. Right. We can't see what's going on further away. Okay. Let's do this one more time. So we remove those. I'm going to run it with a few more particles, and I'm going to see if the larger particle simulation will still do the same thing. So we're going to run with 1,000 particles. And essentially, I'm just looking for the large cluster movement. That's what I'm looking for. This is actually, okay, look. I realize we started today's stream. I had a clear intention of where I was going to go today. We are not going there. This is going to take a little while to plot, by the way. We're going somewhere else, but that's fine. I'm happy to move. Like, I'm happy that like the shared memory code that we wrote isn't completely awful. You know, like I'm happy with that. So I want to do one more thing, which is just going to be flipping the axes, see if we get any speed improvement from doing that. Again, I'm not convinced we will, but we might as well try. Plot with larger dimensions if you can. With more particles, it will have a larger extent. Right, I can do that as well. Oh no, what are you oh knowing? Is that because I dropped something? I definitely just dropped. Like, I have this remote for my light, which I don't think even works. Does it work? Oh, it works. Okay. There we go. Got it back on. I didn't know it worked. All right, let's take a look at Mirage here. Okay, yeah, we can look at larger extents in just a second. So here you have these guys all moving around, and I just want to see if it drifts in the same direction. It seems to be drifting in the same direction, which is really weird to me. Yeah, that's really weird to me that it's drifting the same direction. I mean, we can plot with larger extents, but I just don't think we're going to see anything more with that. Why would it drift in that direction? It's drifting closer to 0. But why is it drifting closer to 0? Your 0 is in the center of the field. But why is I just don't understand why it's drifting the same way. That's what's getting me. Are we projecting incorrectly? I mean, we could be. We could be just projecting incorrectly. I'll try plotting with a larger box. .gp, and let's make this to be 4, 4. Let's do GNU plot. Are the points randomly generated? It could be RNG. It could be the RNG. Could the RNG be biased? They are randomly generated. We could make it so they're not randomly generated, and have them initialize on a grid. Yeah, let's do that. Let's have them all initialize on a grid, just to see if we still get the movement. It's nice to have them all initialized that way anyway. While this is running, I'm going to be right back. Give me just a minute. Sorry about that. Albino Amzel, thank you so much for following. Really appreciate it. Okay, so let's go ahead and take a look at Mirage here. This was in a larger box, and let's just give it a go. Okay, so in a larger box, let's see. It's still drifting. Seeing if it drifts more. 1 second. So, okay, so the two things I want to check here is one thing I want to check is if this happens in lower dimensions as well. So I'm going to try the R-cubed force law in lower dimensions, see if it does this. And I'm also going to try with just a grid of points, because it could be like there's just a random cluster that's generated for some reason in some location. So let's try that. First, we're going to do lower dimensions because that's easy. So let's go ahead and remove this guy. We're going to run this. And we're going to run it in dims equals 2. And see what we get. Again, guys, if you have any comments, questions, concerns, ideas, anything like that, feel free to let me know. I'll totally address it as soon as I see it in chat. It's currently 5 o'clock p.m. my time. I'm going to be streaming until 8 o'clock p.m. So we've got another 3 hours. I've been streaming for 2 hours already. So we're just before the halfway mark of stream. Again, I'm happy to do this. I'm actually really excited to see where we go with this. I don't know why I continued with 1,000 points there, but that's okay. So let's do GNU plot, and then plot 2D. Okay, 2D.gp. Give it a second and see what we get. Again, I don't know if I'm expecting this. If this drifts, I don't know what that means. I don't know if this helps with anything or anything. Yeah, I really don't know what to do about that. But also, would a 1 over r cubed force law... okay, here's a naive question. that I don't really have an answer to. If our force law is actually GMM over R cubed, right? Doesn't that... It means the center mass, right? That's what it could mean as well. But the question I had was, why did it drift downward both times? But doesn't this mean we're allowed to have... Okay, this is a stupid question. I don't really know the answer to this. But is it actually okay to put an absolute value over that R cubed? Why is that okay? I don't know. I don't think that's okay. I think this can be positive or negative. And I think that we have to accept that. Because the only reason this is naively positive is because I guess the square root could give you I don't know. Because R is distance. 1 second. Because R is distance, but distance can be negative, can't it? Do you consider relativistic effects? Clearly, it can't be right to use the current positions of all other stars for one star if they are many light years away. Wait, why not? Wait, actually, I don't understand that argument. Let me think. Distance can't be negative. Okay, I'm sorry. I didn't know that. What can be negative then? Wait. Try using Minkowski distance. I don't want to go there. I really don't want to go there. A negative R would result in positive force, which would be repulsive. Right. Okay, but yeah, okay, you're right. You're right. That makes obviously you can't have a repulsive force of gravity. All right, let's go into Mirage. Here, okay, so here's all the points. They come together. Why is it already rotating? What's causing that initial rotation? What is causing that initial rotation? Also, it does look like the cluster is moving. Why are they drifting? Or the Hamiltonian, which goes 1 over x squared, y squared, and derive the equations of motion from there. I don't want to. I'm sorry. I'm not going to do that. I'll do it later if I have to, but I really don't care if it's that physical right now. Specifically because 1 over r cubed force law doesn't, it's fine. I don't know why he's drifting. That's weird. If star A is traveling with 100 kilometers per second, star B is x light years away. Well, that's because I'm moving. No. I was scrolling backwards. Sorry. This is as far as we go. That's what's happening. Are you sure that's not a projection artifact? Well, right now we're not doing a projection. So we're doing no projection at all. So it's just drifting away is what's happening. So we're doing absolutely no projection. So this is a full simulation here. I was scrolling backwards, so I was looking at it again. If star A is traveling with 100 kilometers per second, and star B is x light years away, let's see. Star B sees the gravity force of star A when it was at position x light years before the current position. Yes, that's true. I was not going to consider the relativistic effects, but maybe I should. And maybe Alcrest is right here and that we should be using some sort of Minkowski space or something that might account for that. I genuinely don't know. But anyway, I'm scrolling the simulation back. So in this case, the whole simulation is drifting, which I don't... There's two things I don't understand about this. Like, one, why it starts rotating to begin with, and two, why the whole thing drifts. But still shouldn't drift in 2D, right? Do all the particles have the same velocity created as pairs of opposite directions? They have no initial velocity. There's no initial velocity in any of these, regardless of power of r. Right. I don't know why it's drifting. I genuinely don't know. So there must be something going on. I don't exactly understand what. Let me just double check the code here. Okay, so we're going to do VI back into the source and forces. Here we go. And we're going to do, let's see, we have the force of gravity 4D in here. It's going to be the absolute value of this times that times that. So this is going to be just r cubed, right? So it's going to be one position minus the other. So we're just adding all these r's together to get our r cubed value. And then we're going to do cubed root of r cubed. Is it supposed to be cube root or square root? Does it matter? I guess not. Yeah, I guess it doesn't matter because r cubed is always... Should it be cubed root of r cubed or should it be square root of r cubed? It must be cubed root, right? It's going to be x cubed plus y cubed plus z cubed, right? And so if we have x cubed plus y cubed plus z cubed, and then we go from there. I might be incorrect, but if the particle positions are not symmetrical around the center of mass can move anywhere. I guess, yeah, I think you're right. I think you're right about that. It's a scaling factor, so it should be similar to changing the mass, right? Let's start with okay, let's do the other thing then. Let's go ahead and initialize these guys on a grid, and let's just get that grid simulation done. So let's go into VI source and then initialization here. So right now we're just returning like random initialization. I guess what I want to do is init type, and like init type equals like rand or something like that. So let's go ahead and put this down to the next line, and let's create another initialization scheme that will basically create a series of points equally distributed along like x, y, and z axes. So we're going to say init type. One second. Is it raining again? No way, it rains like every day here. It's crazy. Equals, and we'll say rand. I don't like that one. But that's fine. We'll allow for a different type. So we're going to go if init type, one second, is equal to rand. We do this. And there. Okay, I could probably create like some sort of initialization function that's just like rand on particles, but fine. I guess we need an else. I forget if there's a space or not every time. Else if. Okay, so now we need to return something. Let's see, what do we have here? I guess it should have a big effect. Stars are moving with up to 8% of the light speed, and the diameter of the Milky Way is 105,700 light years. Okay, that's totally fair. Okay, so maybe this is something we consider in a bit. Essentially, yeah, okay, let's see. It depends on how hard it is to incorporate, right? I mean, how hard it is to incorporate. Okay, right now I don't know what to do to add that effect in, I guess is the actual answer. If I knew how to do it, maybe it's like a very simple change, and I'm not really sure. Like, I'm sure it is, right? Like maybe it's not, actually. I really don't know. But I guess let me reread the comment that you said before. If star A is traveling with 100 kilometers per second, and star B is x light years away, star B sees a gravitational force of star A when it was at position x light years before the current position. I mean, the only way I see to account for that... Yeah, the only way I see to account for that is if we like keep previous time steps or something like that. Like a lot of previous time steps, actually. Which would be incredibly computationally inefficient, I would say. But if you take the cube root of r cubed, wouldn't you just be getting r? My English is failing me here, and am understanding this wrong. No, you got that right. It should be the cubed root of r squared, r cubed. That is actually correct. 1 second, let me take a look at that. Rank quit, forces. The difference is that this is going to be the cubed root of x cubed plus y cubed plus z cubed. So it's not just, so r here is going to be all of them put together. I wouldn't need more memory than the output of the simulations. Wouldn't need more memory than the output of the simulations. Well, I mean, obviously, you know, I think the output of the simulations are actually like less memory, right? Because like you can choose which time steps you output, but also like you run into a situation where like, it's not like you can just read in a file every time step. Like that's an insane amount of time. You know, plus you'd have to read in more than one file. You'd have to read in hundreds of different files. But this is actually a good question. I don't know. I mean, do people do n-body simulations with relativistic effects? Actually, okay, let's do this grid initialization. And then after that, let's look into the relativistic effects. Because surely people have solved this problem before, right? I didn't see it in the papers I was looking at, but maybe it was just one of those implied things. Maybe people were like, oh, everyone does this, you know? But I'm sure people have done this before. If you want to take account gravitational travel time, then simulation of the gravitational waves would be cool. Right. The problem is we're running into would be cool, which is true. Definitely would be true. All this stuff would be quite cool. But also the question is it actually interesting research-wise? I think obviously people must have put relativistic effects onto n-body gravitational simulations. Like I feel like someone's done that before. And I feel it's super inefficient, but that I think would push something somewhere. Like that would be useful to some people. I think like really useful. And maybe the best way to do that is actually to put some sort of gravitational wave grid or something onto the simulation you're working with, like a combination between like a basic PDE solve via, I don't know, finite difference time domain or something like this, and the n-body simulation. That would be quite interesting. And I could see that being quite useful. Again, I don't know how they do it, but however they do it, finding a way to speed that up would be useful for a lot of people. So basically, we need to figure out what the most useful thing is to do. For my own research benefit, what I want to do with this, just simply optimizing n-body simulations is all I want to do, right? So I don't need to delve too deeply into the gravitational wave stuff, all this kind of stuff. But if it's a problem that seems like a fun thing to solve, like a fun side problem to look at, I'm actually really happy to do that. I think if it's something that we can look at, and I can just look at immediately and be like, oh, actually, I have a unique idea of how to optimize this particular code base, then of course I'll do that, right? So that's kind of where I'm looking at here. I'm deciding what is, first of all, the most physical here doesn't exactly matter too much because we're doing it 1 over r cubed force law anyway. It's kind of like, okay, fine, like it doesn't have to be too physical because like it's not physical. No matter what we do, this is not going to be physical. But if there is something that is actually interesting for a group of people outside of like higher dimensionality to Barnes Hut or something like this, then I don't know. I could see that as something that we would want to look into. That was a weird ramble. I'm sorry. I guess like words are not coming out of my mouth in the way that I want them to come out of my mouth. It's one of those days. I don't know. Like I'm having a series of days where like every word is just struggling to come out of my mouth at the correct time, if that makes sense. So your function, it doesn't make sense. I'm struggling to speak in coherent sentences, is what I'm trying to say. I'm going to keep going, but I'm struggling to speak right now. So I apologize if I say something that's kind of just wrong. I'm doing my best, but it's kind of like all over the place right now. Okay, so we're going to create a function here, which I guess we'll call like boxgen, which is going to read in, else if it's probably missing a condition. Yeah, we're working on that. So init type, sorry, you're right, is going to equal to box, I guess is what we're going to call it. So boxgen, we're going to return boxgen, and it's going to read in, I guess, just boxgen of n, and then dims equals, I guess dims is equal to 2 is fine. Okay, so boxgen here is going to read in n, and then dims equal 2. Okay, I should not have set that equal to dims. Dims equals dims. Okay, let's go in here. Dims equal 2. Put a semicolon in there and end that space there. Grid. Oh, grid works as well. Boxgen grid. That makes more sense. Thanks for that, by the way. So let's go here. Grid gen. And in here it's going to be grid instead of box. Grid. Perfect. Okay. So what are we going to do here? We probably also want, in addition to grid gen, we have a number of particles, we have the number of dimensions. So I guess we just want to find a way to equally distribute those particles in our simulation. So for example, if you have 100 particles, okay, how is this going to work? So if you have 100 particles, 100 particles is going to be equally spread out. If your box size is 10 and you have 100 particles, they're going to be 1 apart. How do you know that? Because you have a number of dimensions, and then you also have a box grid extents is what you also have to read in. So here we have grid extents. Okay, is equal to 1. And then array type as well. Is equal to array. All right, let's go in here and let's add all those optional arguments in. So we have grid extents is going to be equal to grid extents. Then we have array type is equal to array type. I'll put these in the optional. Array type is going to be equal to array type. Okay, so how are we going to do this? I think we can find the step size, and then why do I suck so much? Okay. How are we actually going to do this? We need to figure out how many points are going to be distributed along each dimension. So like 10, 10, 10 or something like that. So do I just take the number of particles like this? Do I just do axis num or something is going to be equal to power of n, and then we raise it to the dims dimension? I think that 1 over dims dimension. Is that how it works? Power of 2, 2 is obviously going to be, oh, power is not defined, really? Power mod. Wait, how do I take something, how do I raise something to some other power? I guess it's just going to be n raised to the 1 over dims dimension, right? So n raised to the 1 over dims dimension, right? And then we probably want to, what do we want to do? We want to, that's probably not going to be a whole number, right? Yeah, that's what I should have done. So it's going to be n raised to 1 over dims, and then we want to seal that, I guess, and cast this onto an int, I guess, there. So this will give us the number along each dimension, and then all we have to do is we need to find the distance between each point. And so what we're looking at here is going to be dx, I guess is what distance, whatever, is going to be equal to grid extents divided by axis num. Okay, and then what we have to do is create the array of positions. And then I guess we're just going to put zeros in for the velocity and acceleration for now. We can modify that later, but 0 in for the velocity and acceleration makes sense for me right now. So we have the dx, we have the number. So what I want to do then is I want to try to figure out how to create an array, which is a range. Maybe I just do the following. Maybe I say, how am I going to do this? So A is going to be equal to array type of this guy, and it's going to be n. And what are we actually looking for here? So we have the grid gen n, so this should be a position. So these should all be like floating point values or something like that between each element. So what we're looking at is grid extents divided by 2, and then we're going to have a plus times, and then it should be something like I, wait, I'm trying to think about this, I times, oh gosh, come on, this is not hard, just have to think about it. So we're going from dx to axis number in steps of, looks like some people did relativistic n-body simulations, nice images, lots of complicated formulas. I'll take a look at that in a second. I wonder if this could be, if this could speed up the simulations as well, because for a realistic simulation, all fields are only local around the star, but might need lots of memory. I don't know, I think this is only going to slow it down. I don't see how this could possibly speed it up, but I'm interested in looking at it. Okay, sure. Let me open up here, Zernal PP, downloads, and then Martin cuts.pdf. Okay, I'm interested in this archive. I'll take a look at that a second. Perfect. Okay, so let's go here. Let me just figure this out. So journal new page 4. What do we have here? We have a box. And what we're trying to do is create a bunch of particles that are equally spread across the box. So we have 1, 2, 3, 4, 5, 6, 7. And then 1, 2, 3, 4, 5, 6, 7. Perfect. They're equally spread across. So how does this actually come into code? What we have then is we have a grid extents, which is going to be the size of this grid. 1 second. Pretend this is an equal square. I know you're going to have to suspend your disbelief for a bit, but fine. Okay. So the grid extents is going to be this guy. So it's going to be grid extents. GE is what I'm going to call it. We know what the dx is. dx. And we know how many particles we have. So this is going to be your number, which we called axis num or something like that. Axis num. I don't know why, but that's what I called it, axis num. Okay, so now what I have to do is figure out how to create this array such that we have particle 1. This guy's going to be at negative grid extents over 2, and this is going to be at positive grid extents over 2. So what we need to do is negative grid extents over 2 plus, and it should just be dx times I. Yeah, it should be dx times I. Yeah, we already have dx. So it should just be this, a grid extents, negative grid extents over 2 times, so it should just be negative dx times I times grid extents over 2 for I is equal to 1, 2, actually it should be, maybe it should start at 0? Axis number, should it start at 0 or should it start at 1? 1 to axis num. And then we're going to have to do this again for j. How do I do a double for loop? Because this is going to be this dimension for I, and then it's going to be this here, and then it should be the other dimension for j. So the position is going to be, oh, but it's going to be I, j, k, l, m. Oh, crap. This could be n-dimensional, right? It's not just 2 dimensions. It could be up to n dimensions, where n could be infinite. Okay, well, let me think about this again. Oh, boy. Let's go. Okay, so if n can be up to infinity, in principle, obviously we're going to run out of memory at some point. I think it should be dx is equal to grid extents over axis num minus 1. You're probably right about that. Let me think. So axis num is going to be, the grid extents are going to be like, let's say 1. So the axis num is going to be the number we want across the axis. We can try minus 1. It doesn't really matter here. Okay. I mean, you're right. So we have that. Okay, so now my question is, how do I make an n-dimensional loop? One that can go across all the different dimensions here. It's going to be 4-dimensional or n-dimensional, up to n dimensions. I could have a separate loop for each dimension, but that seems kind of a bit dumb. So these are all going to be, it's going to be your x position, your y position, and your j position. X, Y, and Z, and W positions, for example. And so you have your X positions, then you have your Y positions, and you're going to have to loop. Oh, why am I so bad at this? You're going to have to loop through. I'm really bad at this. I'm genuinely lost. Okay. Welcome to Leo's Labs. We promise 4-dimensional gravity simulations, and you actually get just me trying to put position points on a grid. That's it. Can I just look up code? At this point, I just want to look up code. Okay, so we have how to create an n-dimensional box. How do you create an n-dimensional box where each particle is equidistant apart? I'm going to take a look at this later. Remove that. I should not have removed that. Should not have removed that at all. Okay, let's fix this again. So let's do Zertle, pp, downloads, and then it's going to be Martin. Here we go. I'll take a look at that later. There, remove all unfinished. Okay, let's just do create n-dimensional grid of equally spaced particles. Surely we'll find something, right? For loop Python generate grid of equally spaced particles. Okay, I mean, fine. But this is only going to go through... Also, you're using append? No way. Yeah, this is what I was going to do. That might be complex. Right. Let's go here to H. I mean, kind of. How to generate K points evenly spaced in a unit cube. Okay. Packing and covering. It also looks like some aspects of more general case to be covered in a book. Find it packing and covering. Wait, what? To see that calculation, the best case is not trivial. Look at the paper. Dense packings have equal spheres in a cube. No. Don't give me this. This is not something I want to look at. Oh no. Okay, let's take a look at this paper. Maybe I didn't understand what the Stack Overflow was saying. Let's read this. I'm trying to generate K points that are evenly spread inside a fixed space. I figure a unit sphere or cube would be easiest. It was easy enough for 2 dimensions, but a lot harder as we go up arbitrary dimensions D, unfortunately. I think this is done in a quasi-Monte Carlo methods, but I've been unable to find a formula. No, 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 no. Stop it. Ah. Okay, let's just do it. Let's just do it. We're going to get this done. We're going to do it. Okay? Also, it should be dx times I minus axis num over 2 times grid extents. Dx times I minus... No, you need something from combinatorics probably. Okay. Let's take a look at this PDF. Shouldn't it be dx is equal to grid extents over x? Oh no. Also, should it be dx times I? Should it be dx times I minus axis num over 2? I minus axis number. So the axis number is going to be 7. So you're going to do I minus axis number over 2 times grid extents. Dx. I think you can just keep adding dx's, can't you? Oh, this is clearly wrong. Yeah, this, whatever I wrote here, you're right, is clearly wrong. I get that. I totally get that. This should be plus dx times I. Whatever I had written down, you're totally right, is wrong. But I think this is fine. You start here, you just add dx, 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 right? So 1 dx, 2 dx, 3 dx, 4 dx. I think that'll be fine. You're right that what I had written down was wrong. Let's go here and there. In principle, I think that's right. Negative grid extents over 2 plus dx. Yeah, but you're right that what I had written down was wrong. Okay, here's what I'm trying to do. I know this is stupid. I'm trying to write an n-dimensional code that allows for me to create a grid of evenly spaced particles. That's it. Just create this grid of particles that you see here. All these particles along here. Obviously, I can do it for n when n is known. So if I know it's 1, 2, 3, or 4, I can do it, no problem. Or even up to 5. That's fine. But should start with I equals 0 instead of 1. I think you're right that it needs to start with I equals 0. I think you're right. I was contemplating that as well. Yes, you're right. It should start at. Yeah, you're right. Okay, well, this is going to be fine for one dimension. So let me read this paper now, apparently, because now I'm interested in what this paper is. All right, let's go here, open up a new terminal, type in Zernal pp, and we're going to do downloads, 1786. Where is it? 1786 PDF. Okay, dense packings of equal spheres in a cube. No way. No. Don't give me this. 2004? You're telling me 2004 is when people solve this problem? No. I do not believe that. I genuinely do not believe that. Let me take a look at this. Dense packings of equal spheres. Let me look this up on Google Scholar. I'm getting really... Okay. I'm going to get really, really technical about this really quickly. Okay, let's go to Google Scholar, shall we? And let me see how many citations this dense packing of equal spheres in a cube. Yeah, let's see. Dense packing. Also, maybe this is a different problem. No citations, right? Come on. Julie's one base. I know that Julie's one base, but you can technically index along 0. Okay. Dense packings of equal spheres in a cube. Let me see what this guy has. We're going to go down here. Where are we? Are you... Okay. I think they're doing something different than I wanted to do. I'm pretty sure I just want something simple. I don't think this is a hard problem. Okay. Right. Perfect. This is not what I wanted. I'm happy to say this is not what I wanted. This is about, minimizing the distance between all of them. That's exactly what this is. This is a different problem, and I'm happy to see it's a different problem. Because if it was the same problem, I'd be in a lot of trouble about now. But it can't be the same problem. Like, surely people have solved this problem before. Okay, let's go ahead and discard this guy. Here, delete this guy. On limits of dense packing on equal spheres in a cube. Is this the same guy? No, wait, what? Oh, cited by 45. I'm so dumb. I misread that. 45. This is so interesting. It's like, okay, all these guys who are like, I don't know, like all these people who are like, research is too hard. Like I literally just Googled like one of the most basic things a programmer is going to Google, and I found something that's like, hey, this is actually kind of interesting. You know, like sure, okay, it's not like the coolest thing ever, but like the fact that this was only published in 2015 is kind of interesting to some extent. You want to generate grid of positions of any dimensions, right? That's all I want to do. It's not going to be hard. Like I know it's not going to be hard. I just want to see some source code because I don't know how to deal with n dimensions. Can I create a loop of loops? Because I mean, for this, I can literally like for 2 dimensions, this isn't hard, right? I think I can just do ij. Let's see. So grid extents over 2 for dx over I. Packing in logistics lots of research goes into it. That's totally fair. Is this how to build the array? Is the problem? Right. That's literally. It's not. I don't think it's hard. I think this is actually gonna be pretty easy. So this is 1D already solved. To do this in 2D, I think we just add another for loop and we just say dx here. To do this in 2D, what you want to do is grid extents over 2 plus dx times I for I is equal to 0 to axis number, I think is correct for 1D. For 2D, you want negative grid extents over 2. So you want to basically, repeat. You need to go through every permutation, don't you? Like, yeah, you need to go through every permutation. So, okay. Maybe it's better to loop through n. It's not that hard, but how you solve it with containers you're doing. My brain deals with memory indexing, right? It's just how to build an array. So should you be looping over each dimension? I could loop over each dimension, that's fine. Yeah, that's what I should do, you're right. So let's go, well, no, but I can't loop over each dimension because I don't know the number of loops to do. That's the problem. So that was a fundamental problem. I could obviously do for I, for j. That's fine. I can recreate the grid. So what I can do is I can create the array to start, and then I can assign each number. The problem with that is that I'm dealing between arrays and cuArrays, so I don't want to just create a cuArray. So probably I create the array first and transfer it to the CUDA device. That's fine, because who cares? This is just the initialization step. It doesn't matter. So I want to create the n-dimensional array to start with, and then I'm just going to loop over all of the elements and just, I guess, just give it, yeah, okay. So I'm just going to do it that way. A is going to be equal to zeros of n dims. All right, so here's our array. And then we just go through each point. And each point is going to have a Cartesian index associated with it. So can I just grab that Cartesian index and then go from there? The optimal sphere packing problem was solved in 1998. Needed 6 years of research. It's the same guys Kepler guessed in 1611. Oh, interesting. But it's only 3D. There are articles about higher dimensions as well. Yeah, I guess to be fair, 3D is probably the most useful one, right? Let's go here, paste that. There we go. Enter there. Oh, interesting. Okay, we'll take a look at that as well. There's some good articles to look at after this is done. So how do I go from linear to Cartesian indexing? Can I just grab the Cartesian index? So let me do A is going to be equal to zeros of 10, 10 or something. Okay, so can I grab the Cartesian index of A of 1? Can I do that? No, that doesn't work. Cartesian index is specifically a... so what I was hoping to do was go through linearly through all the elements, just 1, 2, 3, 4, 5, and then just find the Cartesian index. Because if I can find that, then we're good. So how do I loop over all of the Cartesian indices? Can I just do the following? For I equals, let's do 1, 2, print line I, end. Let's do 1, 2, oh, it's within the loop, obviously. But what if I do 1, 2, 10, and then 2, 2, 14? No, that didn't help either. That did not do what I was expecting it to do. You just scale the index, each dimension, and done. You can do that linearly by modulo total number in the lower dimensions. Oh, that's fair. Yeah, modulo operations here would totally work. So if I do a linear index, then I should be able to just pack it back down via modulo index. So just like modulo back in. X plus y times z plus z times, yeah, right. You're right. Um, okay, but we do have, can I just do, for I equals, for I equals 1 to 10, obviously this is going to, and print line I is obviously going to give us 1 to 10. Okay, so now what happens if I do for I is equal to 1 to 10, but what I want to do is go through two different sets of indices here. So 1 to, this is not going to work. No way this is going to work. 10. Obviously this is syntactically wrong. I'm just trying to think here. 10. Yeah, obviously that doesn't work. We want an ij and k is what we want. Ij, k, w. So we could do 3 for loops, but I want to auto-generate those for loops. We could just do one big while loop. How would we do this modularly? Obviously 2D works just fine. So let's think, how exactly do you go from, obviously you can go from 3D to 1D just fine. So how is this done? So let's say I is going to be equal to, I usually think about it in terms of GPUs, so I typically would think of it as, like usually I think of thread ID X and all this kind of stuff, so it's usually like equal to, it's like block dimension times, oh, okay, let me think about this. What happened there? Okay, let me open up a new terminal. I'm sorry, I don't know what happened. 1 second. There, move this down here. I don't have chat anymore. Sorry about that, I'll fix it. IRSSI, join LAIOS labs. Okay, let me go and clear the chat as well. Sorry, I lost chat, but I still have it over here on the side. Okay, so let's say we have a grid here, and it's just, you know, 1, 2, okay, try that again. It's just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, ... right? So we can do what Happy Little Rat just said, and we can say, okay, well, that means that index number 10, what is that in X and Y? Well, it's just going to be equal to, let's see, we have 5, so it should just be 10 divided by 5 in the X dimension, and then 10 modulo 5. What? 10 modulo 5? I think I did that wrong. 10 modulo 5 gives you the leftover. So that tells you how much you're indexing in that dimension. I think I screwed it up. For I is equal to 0 to total points, X is equal to I mod width, Y is equal to I mod width times height, Z is equal to that, etc. If my brain, no, you're totally right about that. I just need to think about how to do that for like N, where N is like 25. Like obviously you're not going to get up to 25. So yeah, we can definitely do that. It takes a little bit of thought. We can do that. Is there a way to create a set of indices to loop over? Can you do for I is equal to 1 to 10 and Cartesian? This is what I'm thinking about. Yeah, we might be able to Cartesian indices. Oh, maybe. Let's try Cartesian indices of A. That did create a bunch of Cartesian indices. So maybe we have this set of Cartesian indices here. So what if we do Cartesian index of A1? Wait. Cartesian indices of A gives you the list of all the indices here. So can we convert them all to like vectors or something and then use that? So we have the Cartesian indices. So since we have the Cartesian indices, we should be able to loop over those. That's what I wrote, basically. My brain doesn't serve me names for things, sadly. No, you're totally right. We can definitely do that. I just need to think about it. I'm like at this weird state where it's like, man, I didn't have to note how width, height, depth. Yeah, right. We have the list of Cartesian indices now, which gives us our I, J, and K. So we can find the I, J, and K. That's fine. So we have the I, J, and K, and now we have the Cartesian index at every linear number. And so what we need to do then is multiply that by dx for that. You can index vector array with Cartesian index, right? Wait, can you just do Cartesian index? of, let me just go over here to Julia really quick, right quick. Julia, so A is going to be equal to 10, 10, 10, 10. So Cartesian indices of A here. So obviously this is our set of Cartesian indices. So we can index with Cartesian index. So how would I do that? Would I do for Cartesian index of I is equal to, wait, can I do for I is equal to Cartesian index of 1, and then oh no, Julia might have a solution available, but it's fun enough to solve. Right, I agree. Cartesian indices, not index. Right, but what I'm trying to figure out is how to index out. So how do I set A or I as a Cartesian index in that? So what I can obviously do for I is equal to Cartesian indices of A, and that'll work. And then print line AI, and this will solve that issue. And in here, so there's all our Cartesian indices. Then we have a set of dimensions. So what we can do, here's a proof of 3D optimal packing. Oh, okay, only 121 pages. I'm not gonna click that. I'm not even gonna scroll through it if I did click it. Oh my gosh, 121 pages. That's insane. Okay, so we have all the indices here. So if we have all the indices, then what we want to do is convert that into something we can actually manipulate. So let's do Cartesian index of, let's do 1, 2, and multiply that by 2. Can we do that? That does work, but it's still a Cartesian index. So how do I get that out of Cartesian index? Can I do array of Cartesian index here? No. How do I get something from a Cartesian index into a tuple? I guess I can just do this where it doesn't matter. It doesn't matter because we have the Cartesian index and we can just directly index A. So if we can directly index A and we know what the... No, it does matter. Cartesian index of 1, 2, 3, 4, sure. And now we're going to do that, and I want to convert this into an array or a tuple. So can I just do tuple? No way. Oh, that worked. Okay. So then our location, so then we have the tuple for this. So we'll have that, and we want to multiply that by dx. So we're going to do this times dx. And then we want to subtract out, so it's going to be grid extents. So it's going to be like grid extents, which is 1. So negative 0.5 plus that. Dx not defined. Dx is going to be 0.1. Oh, we're so close. Without paywall, has nice images. Oh, okay, I'll take a look. Yeah, let's see. We have a few papers to look at actually after this is done. Let's go here, open this, paste this here, open that up. Sure. Zernal PP and downloads, annals. There we go. I'll take a look at it in a second. Scroll down, remove, close. Okay. Okay, this is so close to what we need. There are no method matching star for n tuple. Can I convert a tuple to an array? No. No, I cannot. Okay, so how do I go from Cartesian index to anything else without grabbing each individual index? Because frankly, I cannot grab each individual index because that kind of defeats... Oh, no, maybe I can. For... Okay, wait. This is going to be... Each particle is going to be at some position, and that position is going to be... Yeah, okay, this will work. Wait, we're getting there. We're getting there one step at a time. So we're going to go through each of the particles. We're going to find a Cartesian index for that particle, which is going to be fine. So we find a Cartesian index for that particle, and then what do? Then we find that Cartesian index, and we multiply by dx, and then we subtract 0.5, and that's going to be each element in our dimension. So we should be able to do the following. Control D. Here we are. So we have the zeros defined here. I don't think that's quite right, but what we can do is we can find the Cartesian indices. So how do we do that then? So 0 is 1 and perfect. So now we can do for I equals, for I in Cartesian index, indices of A, perfect, and here, so we have the Cartesian indices, we're going to say A, we have the Cartesian indices, Mert1312, thank you so much for following, really appreciate it. We have the Cartesian indices, but the problem here, so yeah, we have the Cartesian indices. Oh, this should be fine. So we go through all the Cartesian indices, we multiply by dx. But that doesn't make any sense. So A of Cartesian index. So A of what? Oh gosh, I need to think about this. So the big problem is we have to sum 4 Cartesian indices together. That's what we have to do. So for example, if we're n-dimensional, 1, 2, 3, 4, we have 4 dimensions. We have to sum all those dimensions together. Gosh, why do I suck so much? So we have its position in x, y, and z. So we want A of... I want something like A of I is going to be equal to, like, Cartesian, like, A of, like, I colon. So, you know, we set everything is going to be equal to, it's going to be equal to, like, I times dx minus grid extents over 2 or something. That's what I'm looking for. So like a dot equals is something like this. So what I actually want to do is I want to loop over. I want to loop over n is what I want to loop over. And then I want to find the Cartesian index at each of those positions. So we have n particles and each one has a bunch of different dimensions. Dang, we're so close. We're so close to getting this solved. I just can't figure it out. Also, we know how to solve a sphere packing in 8D, but not in 5, 6, or 7D. Oh, that's interesting. How come we know that? So we have 4i in Cartesian indices of A. So A of I colon is going to be equal to that. So we just need to find its x, y, and z location. Oh, gosh, come on. Your axis number, Cartesian index of A dot times dx dot minus field extents over 2. Yeah, I think that'll work. But my main issue is now what's Cartesian indices? So like, my problem is the Cartesian index will give us, where are we? Our Cartesian index. We want to index over this grid, but we're putting it into, so we have an x location, a y location, a z location. An x location, y location, a z location. So I think maybe it is fine. We have the x, y, z location, x, y, z location, x, y, z location. So I think maybe I'm thinking too much about this. Maybe A of I is going to be equal to this, and that's it. I times dx, dot times dx, you're right. Dot minus. And maybe that's it. Let's try it. So now we have A of I, and then we should be able to just go down here and say, if that's correct, we will only need to convert it to matrix, I guess. Yeah, so now what we need to do is say return particles of array type of A, and then we want to just do array type here, these guys. And then that should be fine, I think. Okay, the only other issue here is that n might need to actually change a little bit. It might need to increase. depending on whether it's divisible or not by your like axis number up here. So if axis number is going to be the ceil of int, so like for example, if you have 100 points and you want to split that up into a 3D array, that doesn't evenly split up into 3D, but if you have 1,000 points, that does, right? Are dx and grid extents vectors? They are not. You're right. You're right. This one is, that should work. Wait. I is a vector, grid extents is not. So I think we can just do that, which is what I had before. I think that'll be fine. So neither of these are vectors because they're constant in both dimensions. Okay, so now let me just redefine n. So n then needs to be rounded up. So the axis number is equal to that. So what I'm going to say then is I'm going to redefine what n is and say that n is now going to be equal to axis number raised to the dimension. And this is just going to redefine what n is just to make sure that we're not, confused about it. But this could change what n is for future. Yeah, okay. So if n is not directly, like if n is not exactly on, if n is not exactly divisible by the dimension number, then we need to, or like if n is not a power of the dimension number, then we need to change n for the rest of the simulation in that case, right? Or we just stop. Fine, okay, we just stop. We do our best to fill it as evenly as possible. And if we don't, fine, we did our best. Like that's what we'll do. All right, rain quit. Yeah, let's just stop. Like it's easier. And whatever. This is for debugging purposes. I'm relatively happy with that. Okay, so we have the initialization here, which can now read in the init type. Let's go here. Let's go into vi source, simulate, and we're going to allow to read in the init type here. There, which I hate this. I hate this so much. Init type is equal to rand. Oh, come on, stop it. Rand here. And then for the initialize in here, we're going to do init type is equal to init type. Yeah. So let's just go here and mention. So what do I do here? So if axis number. Okay, so here's I guess what I should do. Axis number is going to be equal to this guy. Yeah, this guy. And then I'm going to say if axis number. I guess I'm going to do the following. If axis number not equal to ceil. Oh, I don't know. Is not equal to ceil of axis number. End here, and we're just going to say print line, and then we're going to say axis number is equal to the ceil of axis number. I really don't like that. My brain is apparently quite fried right now, which is fine. Like, hey, brains get fried. It's fine. There's some special property about 8D, and then a huge jump to 24D, but we have no proof in between, and I don't think we yet know what's so special about 8 and 24. Okay, yes, so one of my friends was talking about this, and I genuinely had no idea what they were talking about. And I'm just going to say, cannot evenly divide n in, well, let's just do, I'm going to do it this way. Space n space into space dims dimensions. Exclamation mark. There we go. Perfect. Okay. Let's see what happens. Rain quit. So now we have in the simulate file, we have the ability to read in the init type. We have that init type. You want a space before into. Yes, you're right. Okay, so next I'm going to do Julia double dash project. And now we're going to do it using this guy. Whew, I'm super tired. And I missed a comma. Okay, let's fix that. Sorry, it's gonna break. Yep. Yep. Let me just do this over here in this Julia session. Julia -- project. Now we're using CUDA and Galilee. Hopefully it will compile this time. If not, we can fix it, and then we'll see what happens. 3 hour of stream. You must be tired. Yeah, look, I'm doing my best. Like, we'll be doing, you know, I'm trying to do longer streams and stuff like that. So I still have another 2 hours of today's stream. What am I missing this time? Initialization.jl. I'm doing something dumb. What did I do that was dumb? We are missing this on line 24 here. Init type. Oh, I forgot a comma there. Try it again. See what happens. But yeah, I'm at 3 hours of streaming right now. Still broke. What broke this time? It is line 25, the very next line. There's a double equals here. Try it again. I've got a feeling that this is not going to like the, it's not going to like the, what is this? More than one semicolon in argument list, or, wait, what? What's going on now? Syntax, more than one semicolon in argument list around this guy. What? Syntax, more than one semicolon in argument list. What line is this? This is going to be on line, loading. It's going to be line simulate.jl3. Okay. Oh, there's more than one semicolon. That's what it means. Okay, try it one more time. We're in the file that's actually running the code. So like we're slowly working our way to the actual thing that's broken, which is good. So that ran. Let me try really quick just to use the initialization function. Or we could just try to run it really quick. Maybe we just run it really quick, see what happens. And here we're going to do init type is going to be equal to, what's it called again? Grid? There's no way this is going to run. Yeah, there's no way. I thought it wouldn't. Okay, what's the issue here? No method matching star for Cartesian index 2, float 64. That's what I thought. Okay, so I figured that was going to break. We need to... Okay, let me try this again. Let's go to quit. Let's run Julia. So we're going to do Cartesian index of 1, 2 times 2.0. That's going to fail. But if I do 2, that will succeed. Okay, great. So can I do tuple of Cartesian index times 2? No, that doesn't work because we can't multiply anything by a tuple. Okay, so then in this case, what do? We need to do some sort of floating point arithmetic, but we can't because we can't cast a Cartesian index. So let's say A is going to be equal to Cartesian index of 1, 2, and then we're going to say length of Cartesian index A is going to be 2. So I can create a separate array and cast it on that, or I can iterate through each Cartesian index is maybe what I should do. So what do we have here? We have the Cartesian index for each location, which I think should be fine. And so then what we want to do is maybe something like no, we're running into the same problem. We're running into the same problem we just ran into. 1 second. So we have the Cartesian index. We need to multiply this by, we just need to cast this onto an array. How do we put that onto an array? So this is going to be very simply I for I equals, A of I for I equals 1 to length of Cartesian index of A. There we go. And then we need to multiply this by 0.1. There we go. That's what I want. And so then I don't think I can use a tuple. I just tried that one, but I can show you it again. So here, when I tried the tuple Cartesian index times 2, that failed. Because you can't multiply a tuple. So, because tuples in Julia are at a different level of U star, not dot star. Oh, maybe. Oh, okay. I didn't think dot star would work. Oh, okay, fine, interesting. I don't know what dot star works there, but whatever. This is one of those things, like, I learned Julia 0.3, and so a lot of things, like, have changed, including the broadcasting operations, and so, like, it used to be way different, and so, like, a lot of the stuff is just, it's completely different than what I'm used to, so I just don't have the right intuition for it. Okay, so in that case, we can use the tuple, and then I can just do that. Let's do initialization, and what we're going to do is go down here, and we're going to do tuple of I, times, I guess, dot times grid extents, and then dot minus, and then I guess I can do the following just to make sure. All right, rank quit here. Let's go over here, Control D, Julia, using, and give it a go. Okay, and then after that, we should hopefully have an initialization function for a grid of points, which is hopefully going to run. So let's do this guy and see what happens. It still broke. Let's see. Cannot broadcast to an array. Cannot broadcast an array to have fewer dimensions. Cannot broadcast array to have fewer dimensions. Yes, that makes sense. So we have the Cartesian index of each point, and what we're looking for. Crap. Okay, wait. We have the Cartesian index of each point, but what we want to do is we have the Cartesian index of each point. So it's going to be like 1, 2. So we're going to be at 1, but we've already defined. So here's the issue. If we get this point right here, this is going to be point, what is that? 3, 4 or whatever. But actually the only thing we want to compute is 3. Because 4 is going to be, so we go through n, and what we want to do is find all the permutations of n, I think is what we want. A of I equals, oh wait, maybe that's right. It should be, wait, A of I equals, no, that's not quite right. It should be, You're right. It's the dot equals is not going to work here. But this should be for I in Cartesian indices of A. No, that's not going to work. This is not going to work. Crap. Okay. Yeah, this is not going to work. We're close though. It's definitely not going to work. I'm almost 100% sure. I'm quitting stream if this works. There's no way it works. It can't, it's impossible. Because it's fundamentally flawed. I can't even explain, I'm so tired, I can't even fundamentally explain. So can it convert object type tuple to object type float 64? Yes, exactly, that's the problem. This is a tuple, and that's obviously a float 64, right? That's the problem. This is what I was trying to explain just a second ago. So what we want to do is we want to go through each. We want to create a set of permutations, and we want to create a set of permutations and go through that set of permutations, maybe? Can we just do permute? What happens? What does that do? Permute does what? What does I do permute to? Permute not defined. Permute dims, permute exclamation mark. Cartesian indices does permutations, right? So we have a set of Cartesian indices, but what we want is a Cartesian. Oh, I got it. We want the Cartesian indices, but we want Cartesian indices of. We want Cartesian indices of just one dimension. Yeah, right. But we want Cartesian indices of. We want axis num No, we're running into the same problem. Ah, we want Cartesian indices of axis num. Can I do this? For j equals 1 to dims? There's no way that's going to work. Does it even work for an array? No. Zeros creates an array, float 64. So it's just, it's basically allocating an array of all zeros is what we're doing. So we have Cartesian indices of 3, 4. So what I need is, like, if axis num is like 10, I need Cartesian indices of 10, 10, 10 is what I need. And then what I need to do is I need to go through and somehow cast that. Can you, maybe we could. What happens if I try that? I feel like tuples are weird, so maybe not. So let's do 10 for I equals 1 to 10. It created base.generator. Can I just, what happens if I do this? I don't think this is going to work. There. And then we're going to have your tuple of I, which is already, okay, your tuple of I times dx. And then we want to do a of I is going to be dot equals to that. And that should do it. That's what we want. Okay, if that works, then let's try that then. Perfect. Yeah, it's super good. If that works, then that's exactly what we need. I think. I'm like 25% sure, which is more sure about anything than I've been this entire stream. After this, I'm going to take a quick break, just like reading some papers or something else, just because my brain is fried somehow. I know this is like a super simple problem, but my brain is just, it is fried. So I need to just chill for a second. No way this is going to run. Oh, of course it doesn't run. Of course it doesn't run. You're missing the call to tuple. Thank you. Thank you. I told you my brain is fried. Let's run this one more time. Control D, Julia, using this, and then we're gonna go from there. My word, I am just like, my brain is like, it's like that repulsive visualization we did earlier. All the particles just flying out of nowhere. Oh, it's crazy. All right, run this again. Please. No. Okay. No method matching Cartesian index of tuple of float 64 or float 64. Why are they float 64? That's the question. Why are they float 64? Because axis num has been sealed onto a float. This needs to be changed to an int. And then we're going to have an else here. It's going to be equal to int of axis num. I hate this. I hate this so much. Shouldn't each of the Cartesian indices be an actual position instead of index to a position? Shouldn't each of the Cartesian indices be an actual position instead of an index to a position? Shouldn't each of the Cartesian indices be an actual position instead of an index to a position? I don't understand. I don't understand how we could make it an actual position. Yeah, I don't know how we could do that. But again, I could just, my brain's super fried right now, so it's probably like super easy to change. The position is computed in the for loop. Yes, that's how it is right now. Let's go over here, Control D, Julia double dash project, using CUDA and Galilee, and give it another go. Whew. Okay. I think we're getting there. I hate this conversion to int. I hate it so much. Let me find another way around this. Okay, cannot broadcast array to have fewer dimensions. Fine. Okay, let's fix this conversion to int thing because I really, really genuinely hate it. Okay, let's go here and do seal of int. And let's do this. So it's now if n raised, I guess, int of n raised to 1 over dims is not equal to axis num, then we do this. Okay, so now we have ints. Okay, so now the only issue is this thing. The position is computed in the for loop. Okay, so the only thing we have left is this broadcasting operation. And this is because we have a Cartesian index, which is going to be, right. So we're going through each of the Cartesian indices. So what I actually need is another value, which is going to be j or something, for I. Is there like an enumerate or something I can do in Julia? Because otherwise I'm going to do something really stupid here and do j equals 1, and we're going to do j plus equals 1 in here. You need parentheses around whatever dimensions that if statement. Thanks. Thank you. Okay. Sure. So we're going to run Control D. Julia, I know there's a way to do a double indexing here, like an enumerate or something, but I just let me get this to run, and then I'll figure out the making it pretty bit in a second. Yeah, I don't know Julia, but I know PEMDAS. Good. Happy to hear that. Okay, error, inexact error, int64 of 31.622. What? Where's that coming from? If int, right. If this is what I'm gonna do then. Control D, Julia. We're gonna run this again. I don't know Julia or PEMDAS. Well, to be fair, like you're helping me out with Julia more than you know Julia apparently more than I do. I'm like running into all these issues. But like, yeah. So let's go here and let's run that. And then, okay, we have another issue. Cannot broadcast array to have fewer dimensions. Okay, then that's what I was afraid of. I have documentation open and the interpreter. That's totally fair. I only have the interpreter and my brain, which is not interpreting anything. Okay, so we're going through each index in A, which is going to be, so axis num, let me grab this guy. What does this actually do? Let me grab this really quick, run it over here, and we're gonna change it so this is equal to 10, and we're gonna do this so it's equal to 2. Let's do 2. Okay, this creates 1, 1. It's a 2-dimensional array that goes up to 2. So if we do this, it should be, it's now a 3-dimensional array, which is what I wanted to see. Perfect. It's a 3-dimensional array with 2 as the index for each one. Perfect. Which means, what I mean is looping over Cartesian indices generates 1, 1, 1, 1, 1, 2. And these could be a list of positions you want, and then you would just have to scale them by n and subtract. Right, that's exactly what we're doing here. So we're trying to go through all of the Cartesian indices like that. So it just goes through, you know, those are all of our positions, and then we're setting that equal to aj. But for some reason, this calculation here is not the right dimension. So this Cartesian index here is going to be going through, like, you know, it's going to be going through 1, 1, 1, 1, 1, 1, 1, 2, like this over here. So 1, 1, 1, 1, 2, 1, 1, 1. It's different, but it's the same thing. 1, 2, 1, 2, 2, 1, all this kind of stuff. So that's what we're doing here. And so this is now 3 dimensions. So I guess my question is, oh, this is why. It's a of j, comma, or colon. Julia double dash project. Okay, I'm like 27% sure this is gonna run. That's high. I've never been 27% sure of anything in my life. This is as high as I've ever gone, and I'm convinced this is gonna run now. This is it. We got it going. It's gonna run. Not even gonna look at the error message. Crap. 1000 by 2 matrix at index at 1001. Right. For I, and then we need one more final thing in here, which is gonna be if j is less than a of size of a 1. Control D, Julia double dash project, using CUDA Galilee. Okay, do we have a grid of equally spaced points? That's all I care about. That's genuinely all I care about. Nothing else matters. You're overrating j in the tuple. Crap. Okay, I hate this. I hate this so much. I hate it so much. I'm doing everything wrong. Also, this should definitely be here. Control D, Julie double dash project. One more time. Let's go. Let's get this done. I'm so tired. Like at this point, like I'm so tired. It's like it's almost like I'm coding drunk. Like I'm that tired. You know, they did some studies. I don't know. I don't remember where I read this from, but I definitely read somewhere that like it's more dangerous to go driving when you're really really tired than when you're like buzzed or something like that. Obviously, if you're super drunk, it's like it's you don't want to do that. But like there is some level at which being tired is worse than being a little bit drunk. So some code better drunk, not me. Okay, I'm sorry. I apparently just write bad code, but some people, when they drink alcohol, all of a sudden their code is genius, you know? Drunk research stream, when? I don't drink alcohol, but maybe. Okay. Hold your horses, guys. Hold your horses. We got it. We got something. We got something to run. It's not going to be correct, but we got something to run. We are running it in 40, dims equals 2. Let's go. We got it to run. It's not correct, but it's running. Oh, no. Oh, come on. Please. GNU plot. Don't let me down. I've heard of people getting DUI ticketed for driving while too tired. That's probably totally fair. Like, honestly, I believe that. So I've heard of Balmer's Peak. What is Balmer's Peak? Okay. So can we give RUIs researching under the influence? This is not a lie. So when I was younger, I was super Christian, right? And I had this shirt that said "Under the Influence of the Holy Spirit." And I got to be honest, I didn't like that shirt very much, but I wore it a lot because it was the only shirt I had that fit me, like was actually fit me properly. God, that looks correct. That looks like we did it. Yeah. Okay. Let's do this again. Let's do it again. Okay, I'm excited now. We're gonna change this to 100 particles. Let's go. GNU plot. Oh. Balmer's Peak is for boomers. Everyone nowadays is microdosing acid. Wait, what are we talking about? I'm completely confused. Do a square number. I just did. Mirage. Look at the... Oh, no. I'm off. What? No. 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 How did that happen? We spent all this time to create a perfect grid. And then it's just what? It's also not even centered around 0. All of that work. Ow. Okay. I don't understand. So this goes... yeah, it's definitely an indexing error. So this is 1 right here, right? So it's going from -1... Okay. Yeah, I know what's wrong. I know exactly what's wrong. Okay, initialization.jl. This should start at 0. And go to dims -1. That's what it should do. Now that it's triggered, everyone's on OCD. That hurts to watch. We spent literally an hour or over an hour trying to create a square grid, and we created we created a grid that was almost exactly not square. It was like almost there. We were off by 1. Okay, I'm pretty sure this will do it though. Remove this guy. Control D. Julie double dash project using revise, and then we're gonna do using Galilee. And where are we? CUDA and Galilee. We're going to run it one more time. One more time. This is going to be it. This is going to be it. We're going to get it. We're going to get a square grid. And then we're going to realize our R-cube forces are bad. That's 0, 0. Oh, no. Okay, so let's do... remove, and run it one more time. Tuple the same size? It should be the same size. We were off by 1, weren't we? This is it. Less than or equal to. There you go. That's it. That's what we got. Less than or equal to. Found it. This is it. This is it. This is it. I gotta run it one more time, but we got it. Remove. Go here. Yeah, what'd I do? Why are you taking so long? There we go. Okay, this is it. This is it. This is it. We have it. We have it. All right. We're gonna run GNU plot. We're gonna get a beautiful galaxy visualization. The most beautiful galaxy visualization you've ever seen in your life. Oh, come on, please. I hope. Just for once in my life, just be correct. I'm just like, I'm so tired. Mirage here. Okay, look. Akris, you're right. I was wrong. You're right. Okay? I don't mind admitting that I was wrong. We're still shifted. But like, hey, we got the point. You know, I don't know why it's already rotating like that. That's kind of bogging me. Yeah, so now we just have to center it around 0, 0, which we can figure out. Okay, so we got to center it around 0, 0. Let's do that. So we're going to do source initialization. How do we center it around 0, 0? We have tuple minus grid extents over 2 because 10 is even. You're just not centered at 0, 0, and it's because 10 is even. It's because 10 is even, so we are... it's going to be grid extents over 2 minus grid extents over 2. No, right, there's no particle at 0, 0. Okay, okay, fine. Let's do this again. Let's grab another square. That's not 100, but this time it's a bit more than 100. What's another square that's above 100? What's 12 times 12? 144. What's 15 times 15? Two of 25. All right, let's give that guy a go. I couldn't. I'm so bad. How can I not remember 15 times 15? Like, oh my gosh. Okay, so we're gonna go here. We're gonna run GNU plot one more time. Take a look at it. Should hopefully be. It's 225. Yes, you're right. 225. I wrote down 225. For some reason, I thought it was 255 when I said it just then. I can almost guarantee, however tired you are, I am more tired than that. So here's my issue. 0, 0 is here and here, so it still looks like the whole thing is shifted, right? Doesn't it? It looks like it's going over 1, and we want to go... We should be going to -1. So grid extents... Okay, wait. It shouldn't be grid extents over 2. It should just be grid extents. Full stop. Because it's going to go from -1 to 1. And then what we're going to do is grid line. In a sense, we're creating grid lines, yeah. Not good grid lines, but grid lines. Okay. So now we have the axis number. Grid extents divided by axis number minus 1. So let's see. The axis number in this case is going to be the ceil of int of n raised to 1 over dimension. So in this case, it's going to be 15. And then we're dividing grid extents by 14. Okay, let's just do it. Just screw it. I don't care anymore. Let's go. See what happens. What's the worst that could happen? Right now, I'm arbitrarily running code and hoping it works out. Everyone knows arbitrary code execution is like, you know, totally fine. No one has ever been bitten by like anything like that before. So let's keep going. Also, yes, I do recognize this is not arbitrary code execution. It's just, I was running code just because I have no idea what to do. I don't even know if I think Merck's 1312 for following like 30 minutes ago. I'm so out of it. So we're gonna do Mirage here. Why am I having so much trouble? Genuinely speaking, why am I having so much trouble? Allowing ACE arbitrary code execution is my favorite part of my job. We're still off. All right, let's see. What else do we have? So right now it's just bothering me that you're right, that there's something wrong with the force law, clearly, which we'll look at in just a second. But now I'm really interested in just getting this to be centered. Let's see. Okay, okay, I know. You have to keep it into grid extent over 2, but subtract an extra dx. Are we sure this is correct? Dx is grid extents over... I'm just making arbitrary changes and hoping they work out. There is genuinely no easier way to write code. Honestly, I might as well just be a monkey at a typewriter, just randomly pressing keys and hoping that they work out at this point. You know, like... Oh man, way back in the day, I wrote this code that was for... that was, you know, like if you have monkeys on a typewriter, eventually they'll write like the works of Shakespeare, whatever that phrase is. Mirage. Is that it? Did we do it? Are we done? Is this it? Does that look centered? I can't tell. Wait a minute. 1, -1. I think we're off. We're off by a single dx. I think we're off by a single dx. Oh, come on. It doesn't matter. It genuinely doesn't matter. Oh, is it dx minus 2? It might be. We might be off by a dx minus 2. I just have to compliment one-way function here. Just, I know everyone else is saying no, but like that's your first comment in the channel. You might have been here before. It's just, I find it really funny. It's just like someone pops into stream and the only thing they say is no. It's like, oh, okay. Try less particles, 64. I could, but I think, yeah, let's go here. Let me just try it one more time. Remove Galilee.run. Oh crap, it's all broken. Everything's, how did I do that? How did I break it? No method matching minus for 2. Okay, no method matching minus, you say. Okay, that's fine. That's fine. Yeah, no problem. Okay, there we go. Minus dx over 2. I think it probably is dx over 2. Hello, lab of Prutz. How are you? I'm sorry. I'm being what's it, persnickety or whatever the word is. We're in GNU plot again. It's still not perfectly centered. I'm pretty sure it is dx over 2. I'm pretty sure you're right. But I just want to double check. I suppose if I had GNU plot output grid lines, that would help as well. I wish I had actual labs. It will also be dx over 2. Yeah, you're right. You're right. You're totally right. Yeah, okay. One more time, and then we're done. All right, grid extents, minus dx. Put this in parentheses. Write that. Go over here, remove the data files, run it one more time, and there we go. We got it. We've solved the issue. We're done. It's perfect. It is absolutely perfect. The code will run. We're going to all be happy with our lives for the first time in ever. You know, it's going to be great. I'm happy to be here with you guys, you know, happy looking at code. I don't know what I'm saying. I'm so tired. You know, that's a funny idea. What's a funny idea? Mirage here. Is it plus? I think it's plus. I think we're still off. I think it's off in the opposite direction. Okay, let's go to this guy, and we're going to add dx. We're going to add dx, and instead of mice, there we go. Write this, go over here. Write this, go over here. Remove, run, over here, quit. GNU plot. Done. We're done. It's perfect. Absolutely perfect. This is exactly what we needed. And then we're going to run the same simulation again. I don't know. We're just going to run it again. I really, the whole point here was to check, let's check 3D. Obviously, we need to check 3D as well. You're correct. Okay, this is centered. Okay? It looks centered. All right? Doesn't it? Here's one, right under one. Here's one over here, just above one. If we go down here, it looks like it's just within 1 and -1, which we said were our grid extents. Okay, I'm happy with that. And here's a visualization. It's wrong. This is all wrong. This thing is wrong. This is definitely wrong. It's somehow drifting. Oh, is it drifting? Actually, wait a minute. It's not drifting. No, is it drifting? Oh, it is drifting. No, wait. Wait a minute. It's not. I can't tell. No, it's not drifting. It's drifting the other way now. Wait a minute. What? No, I was not scrolling back. I was not scrolling back at all. Look at this up here. I don't know if you can read it. 998 out of 1,000. I'm just going to scroll all the way backwards through the simulation. All right, you can look at that counter up there on the top. I'm literally counting back the whole time. It's going to drift up, and then it's going to drift back down again. What? It's oscillating. Yes, it is definitely oscillating, which is weird. Plot the center of mass? Yeah, I can do that. Give me a second. Let me, oh, this is so weird. This thing is just bugging the crap out of me. So it goes negative when we're negative and positive when we're positive. So that says it must be a numerical problem. Because, like, again, why are we just dropping down that way? I didn't give them any initial velocity. So that says to me that we're somehow tied to the x-axis or y-axis. Nick. Unrelated to anything, but does this work? I'm gonna take a look at the link. Oh man, that's so funny. The initial spin definitely doesn't make sense. We're somehow tied to like the x-axis somehow. I don't understand it. Wait, what? How did you put this in the... It works fine. What's wrong with this? Well, you said it doesn't work, but I think it works just fine. So it precesses. Yeah, it's oscillating. So the center of mass. Okay, let's check the 3D and stuff like that and see what we got. Interesting. Oh, this is quite nice. I like that. Good. Also, algorithm archivist, algorithm archive. Sure. Yeah, that makes sense. Good. Oh, that's amazing. Because that wasn't a merged PR. That was like just a test. Okay, we're gonna do this again, except in 3D. So let's change dims to... let's change dims to 3, and then we want something that is a cubed... let's just do 1,000 particles, or no, we don't want 1,000 particles. What's 5 times 5 times 5? That's 125. Let's do... What's 6 times 6 times 6? Julia, 6 raised to the 6th. This is third. 216. Let's do 216. Sure. Control D. Run. Thanks, guys. So what project is that? Are you talking about the project that we're doing right now? Like what's going on up here? Or what project for the algorithm archive? Yeah, it's for the algorithm archive. It's the... you've been here before when we've talked about the algorithm archive. In particular, it's the number of people who are able to do the reviews for different languages and stuff like that. So it's quite cool, honestly. Like I'm really happy to have that in. Algorithm archive is big. It's not super big right now. I mean, we want it to be bigger. And slowly but surely we're getting new chapters in. It just takes time, because we care a lot, or I care a lot about chapter quality. And so I end up like, slowly but surely like going through, each of the steps. Okay. So let's take a look at Mirage. Oh, that looks like a cube. That looks like a cube to me. All right. But we do need to zoom in a little bit. Let me go into, viplot.gp. Well, actually, let's just do it for 4D as well. So what is 6 to the 4 is going to be 1296. Maybe we should do 3 to the 4 instead. 81. 4 to the 4. 256. Perfect. Let's do 256. Okay, we're going to run this in 4D. And just make sure that looks like it. It's going to be a weird looking cube, but it's going to be a cube. Let's go. I meant you don't say a lot when you say it has to do with the algorithm archive. Oh, that's fair. That's fair. It's because I switch contexts too fast. And you're right. That's a very strong criticism, or very like obvious criticism of me when I'm doing the stream. You're right that when I pop into a new topic or something, I should better introduce that topic. So for those of you guys who don't know, and you haven't been here before, let me just go ahead and go over here. So what you just saw was I think a PR for the algorithm archive. This is a online textbook with a variety of different algorithms in it. For example, here's Monte Carlo. And the idea is we try to, first of all, teach Monte Carlo in clear and intuitive way. But also what we do is we allow people to submit whatever languages they want. And we do our best to get these languages reviewed by people in the community to make sure that the code is at least relatively clean. Sure, there could be issues with it because, again, we have to teach the algorithm, so there could be different issues with it here and there. But for the most part, we're trying to make sure that we teach the algorithm with every language that we can. Now, what Nick just showed you was a particular PR for basically making that review process more streamlined. So the idea is that if you are submitting a Haskell pull request or something, and you want to ask, hey, who can review Haskell? All you have to do is go to the list of reviewers and click on that person and say, hey, would you mind reviewing this code? It was a link to your live dev environment. Oh, I didn't realize you had a live dev environment. Super cool. Yeah, good. Okay, so we're gonna run this. I'm still building the algorithm archive. Let's go over here. We have that run. Oh, I forgot to remove the data file, so we have to run it one more time. But once this is done, we should be able to see a 4-dimensional hypercube or whatever. So we're going to do GNU plot here, and let's see what it looks like. Hopefully we see something that kind of resembles a tesseract. That's what we're looking for, a tesseract-like thing. And then we're going to watch it, and then we're going to try to figure out why we have a weird thing going on with the forces. Let me get some water. Super thirsty. By the way, guys, it is currently 6:44 p.m. I'm going to be streaming till about 8, so about another hour. Yes, so what I'm doing right now is I'm doing a 4-dimensional galaxy simulation, which you'll see right now. Oh, 1 second. So this is a 4-dimensional galaxy simulation. What we've done is we've taken a tesseract and we've projected it down to 3D. And then if you watch the simulation, you see all the points kind of come in and they kind of come out like this. Now, what we're trying to figure out right now is why there seems to be a weird drift to all of the particles as they move around. And that's something that we're trying to figure out. So this was, in essence, that n-body galaxy simulation. Now, for the record, for those who may not be following exactly what we're doing, and again, this is a good criticism of what I should be doing, essentially, at every given point in the simulation, we're taking a look at a single particle, and we're looking at every single other one of the particles in the simulation, and we're asking, hey, how should I be moving? Like, how should this particle's gravity affect me as a particle? So this guy is currently moving out this way, but then it will soon turn around to come back into the pile because, of course, it's affected by everyone's gravity, and it should be coming towards the center, right? So that's what we're expecting to see here. Now, when we were looking at the 4-dimensional gravity simulations, we realized that it should be a 1 over r cubed force law instead of 1 over r squared force law. So a slightly different gravity effect, which led to this simulation here. Shadipto earlier in stream mentioned that actually we're doing something fundamentally wrong with how we're doing that calculation, because since we're using a cubed root, in principle, the force could be unnecessarily negative when it should, or unnecessarily positive when it should always be negative. And for that, we fixed it. And then we ran into a weird problem with that. So what we did from there is we created an initialization routine. 1 second, let me play this again. We created an initialization routine. Sorry if I'm lagging a little bit. That would allow for us to create a perfect square so we can do some better testing and stuff like that. After doing that, we realized that there's still a weird drift, and I'll show that to you now. Let's go ahead and do remove, and I'll show you the drift. Maybe we want to do 225, perfect. So we'll show you that weird drift that's going on. Are you simulating Newton gravity? Yes, that's what we're doing. We could be simulating, like there's many other ways in which we could have done this, but what we're doing right now is just simple n-body Newton simulation, 2D. All right, let's take a look at this graph. Then I think all we have to do is fix that force law for the 1 over r cubed. The 1 over r squared force law seems to be working fine. So I'm not too worried about that one. Also, even though we spent 2 hours just trying to create a distributed grid of points, I'm still relatively happy with that because this is going to help a lot with debugging and stuff like that later on. Okay, so if you watch this, note that it immediately breaks symmetry, which is super weird. Or does it? It immediately starts rotating, which is weird. It shouldn't start rotating. Yeah, it shouldn't start rotating at all. And then it starts to kind of oscillate around in weird ways. It's kind of weird as to how it moves. This wasn't what we were expecting. And I think there's probably still a negative sign somewhere, depending on the dimensions. So we'll take a look at that later. I find it weird that it does, because like, why would it rotate down this way instead of coming towards the center? Like, this doesn't make sense to me. The only thing, and note that it's moving down on this side and moving up on this side, and it's positive on this side and negative on this side. And at the same time here, it looks like it's kind of going in just a little bit, maybe not. But I feel like there's some sign error going on. Pretty sure the force is radial. There are no angular component. Right, that's what I think as well. I see you have x86-64 assembly as a language in the archive. Do you consider adding LLVM IR and WebAssembly? So the truth is, when it comes to algorithms in the algorithm archive, the big thing we need to focus on is whether that language can be reviewed by other people, right? So if you can find people, like a community of people who are doing LLVM IR and WebAssembly and stuff like that, and you can find people to do those reviews in the algorithm archive, then yeah, definitely, that's fine to accept. But the main thing is that we really need to get people to, you need 2 people to get something submitted into the algorithm archive. Well, technically 3. You need 1 person to submit the code, another person to review the code, and then me or someone in the algorithm archive dev team to actually merge it in. Reviewability is the thing I'm working on right now. I'm identifying languages that can't be reviewed. Right, that's actually super useful, right? And part of the process here is just getting more people in the community, more people looking at the algorithm archive, and just trying to make it a really useful tool. And the more people there that are trying to make it a useful tool, the more likely it is that we can really make it something that people like and people use all over the place. So like, part of the reason why I'm doing the stream, part of the reason why, I make the YouTube videos and everything is because I know that if we have a community, the algorithm archive is going to be fine. Even if I had to leave completely, if we have a vibrant community of people who are here, that would solve the problem. Like, that's the thing. Like, we're just trying to get more eyes on it and kind of get more people to help with the review process, all this kind of stuff. So if you've seen the algorithm archive before and you're like, I don't really like this thing because of these reasons, submit a PR, submit an issue, let us know what we can do to fix it. This kind of stuff. Now, there was an argument that I heard not too long ago that I do kind of accept, saying that, in order for people to update the algorithm archive, we do ask that they interact with GitHub. And some people really like that because if you're a new developer, the algorithm archive can actually be really helpful because it means it will allow you to use GitHub in a way that you might not have already done. But if you are, maybe not willing to learn more about software development or something, then the interaction with GitHub could actually be kind of negative. It could mean that we don't have as many people interacting with the code. I know at least a few of my friends have never used GitHub before in their life, and they tried to submit code to the algorithm archive, and I just couldn't figure out a way to submit it because we couldn't create a PR for it and do the review process and all that kind of stuff. So I don't know. It's kind of difficult. Supa Jabroni, thank you so much for following. Really appreciate it. Okay, let's go to VI source and forces.jl and let's see if we can figure this out. So the force that we're working on right now that's kind of broken is the 4-dimensional force. We can set up a git patch we can set up git patch setups, but we should probably take that offline. Wait. As far as GitHub, people not linking GitHub because it's owned by Microsoft. That's another fair point. I don't really know how to tackle that. I mean, right now, the majority of open source software, if you're looking for open source software, it's probably going to be found on GitHub. I mean, there is GitLab. There's a bunch of other places that you can go to. But for the most part, if you're looking for open source software online, you go to GitHub. I hate that it's owned by Microsoft just as much as everyone else hates that it's owned by Microsoft. But I mean, what are we going to do? Change it off of GitHub? At this stage, I really don't think we have an option there. It's kind of like how we don't really have an option not to use YouTube. Like YouTube's owned by Google. Not everyone likes Google, but it's like, what are you going to do? I mean, it's not like you can use anything else. And I guess the same is true for Twitch. Twitch is owned by Amazon, but what are you going to do, Anyway, what do we have here? Position LIDK minus position 2 of K. I think that's the issue right there. That's it. It should be position 2 of J, comma K. That's the issue. I solved it. Everything's fixed. Position 2. These need to be changed later. ID. I'll change them in just a second. No, gravity should work. LIDK, J, comma K. Position 2 should be LIG, J, comma K as well. Because position 2 should be... No, it's still LID of K. Yeah, I'm an idiot. LID. This is also going to be LID of K. So basically what had happened was the J actually doesn't exist. So I was remembering from earlier on in stream when I tried to change the way the force laws were implemented so that I could make it run faster. Because if you were here yesterday, you might have noticed that we spent like basically 4 hours optimizing the code. And at the end of all of that, we ended up basically having code that seemed to run 3 times slower. And I was like, God, I was confused. I was like, how could we have possibly, how could this code possibly be running so slow? I was like completely bamboozled, perplexed, whatever you have about it. I had no idea what was going on. And it turns out, so then when I started stream today, I started trying to optimize it, doing all this stuff. I found that the code was still kind of slow. I was like, why is it so slow? And then I realized I was running the CPU version when I was benchmarking for the GPU version. Therefore, I was running the wrong code. And that's why it was so slow. So then I went back to what I did before and basically found that, actually, it's fast. It's fine. It's totally acceptable in terms of speed. There's some other things that I want to do to speed it up. And there's actually a few other tests that I want to do. But I think right now, the way this code currently is good to go ahead and commit. Let's write this. Go here into Control D. Julia _ project. LID. I'll talk about that in just a second. Here. And we're going to do Galilee.run 255 extents dims 2. Perfect. Using this, and then we're going to run it one more time. And then I'll explain what's going on. 1 second. Yeah, I'll explain the code in just a second. Let me just get this running so that there's something going on. Perfect. Okay. Right, so this code isn't particularly it's not super well written. Hey, Screamer Chaotix, how are you? I'm here to lurk and enjoy repulsive simulations. Well, if you're here for repulsive simulations, I've got a bunch of bloopers for you. Okay, so how exactly does the code work right now? Again, this will be optimized. We're slowly in the process of optimizing it one step at a time, but here's how it currently works. This is a kernel that's launched on your GPU, right? So your GPU or CPU has a number of threads. Your number of threads is defined based on the number of cores that you have on your system. So for example, I have 16 cores on my CPU, and I've got any number, 256 threads in each block on my GPU. So we have a thread ID, which is going to go through every single particle in the simulation. So your thread ID is going to go from 0 to 1,000. And then these are split up in individual blocks, each of which have 1,000 local threads. So the way I'm doing this is I'm setting n to be the size of accelerations 2. This is going to be the size of your dimensions. So if your x and y is 2-dimensional, if it's x, y, z, it's 3-dimensional. If it's x, y, z, w, it's 4-dimensional. And then what we're going to do is we're going to create a temp acceleration, temp position 1, and temp position 2. All of these are locally indexed, not locally indexed. All of these are shared memory tiles. So this doesn't really mean much on the CPU, but on the GPU, you've got different levels of memory. You've got global memory, and then you've got thread local memory, and then you've got shared memory. So what this is doing is it's creating a shared memory tile that is of at most 4-dimensional. That's not great, but that's just how I did it. So it's of group size, which is up to 256, and then thread dimensional over here. And so the way this works is you create for each block, you create a grid that is up to 256, up to your thread number, right? And then what you do is you say, okay, for each of the dimensions, x, y, z, and w, we're going to set the temp acceleration to be 0, and we're going to set the temporary position to be what the positions was before. So the reason we're doing this is because reading and writing to and from shared memory is way faster than reading and writing to and from global memory. And so we're putting this onto local memory, some shared memory, so that we can more easily access the data. Now, this is where things get a little bit annoying. What I'm doing is every time step, I'm going through every other particle in the simulation, and I'm asking, hey, what's the new acceleration based on your position with all the other particles, right? So in here, we're saying 4k, 1 to n. So again, all of the particles, all the dimensions. We're then going to say our temp position 2, which is going to be the position that we're comparing against, is going to be equal to positions of jk. So this is going to have us go through each individual particle, and k is going to be our dimension. Then we run the force law with temp position 1, temp position 2, temp acceleration, the local ID, which is going to be your local index along the shared memory array, and then n, where n is going to be your dimension number. Now, the reason we have to do it this way and send the entire shared memory array to the function is because of a number of different things. The main reason is because we cannot create an array while in a GPU kernel. So I can't create a subarray to send in. And this is also why I had to create a giant shared memory tile, one for every single position, instead of just using one position, because otherwise I would have created an array for each thread, but I couldn't do it that way. So this is why I have a lot of shared memory usage in a sense. But a lot isn't that much. It's not a huge amount, but it's a lot, quote unquote. Anyway, so LID is your local ID. It's whichever thread you're working on, basically to index your row in the position, acceleration, and everything. And then n is your dimension over here. So that's kind of what it is. I may not have done a super good job describing that, but that's kind of what we're looking at. Then we have the accelerations down here. So the way I wrote this, I have minimized the number of synchronized statements. I just don't like having a synchronized statement in there, because what the synchronized statement will do is it will pause all thread execution, basically disabling threads from acting until all the threads have caught up to this random barrier, right? So I removed all of those synchronized statements so that this is all basically one thread doing all of its work at one time, so it doesn't have to rely on any other thread. This is advantageous in some ways, but it also means each thread has to do a little bit more work. So I'm not sure actually what the best idea here is. This is why actually at the start of stream I talked about a fundamentally different acceleration method, calculation method that I want to try as well. So let's go ahead and check to see if we still have the asymmetry going on, and then we'll give this a go. So we should be able to run this in 2D, and then we should have a perfectly symmetric visualization at the end. Also, I'm sorry that I went through that very quickly. This is the problem when you're doing GPU engineering. Or like anything, like, programming, to people who don't know programming, it's like, it's hard. You have to explain like a bunch of little things, and I didn't do a very good job of explaining it that time. Sorry about that. Okay, so we have here's our initial set of points. Okay, 3, 2, 1. Nice. Look at that. Beautiful. Oh, that looks super nice. Holy cow. Look at that. Absolutely beautiful. I really like that. Holy cow. That is absolutely beautiful. All right, let me do that again. Let's do one more thing. So we're going to do Mogrify, and we're going to turn that into a video. We're going to watch it one more time. That was very nice. I liked that one a lot. In fact, let me redo the 1, 2, 3, and 4 dimensional simulations so that they're all on a grid to begin with, because I just think they look prettier on a grid. You need to load off a lot of stuff in a short amount of time to people. Yeah, and I do apologize. I need to do a better job in general of just describing the things that I'm doing. I erased a video on accident. Let's do mpv test.mp4. Okay, you guys ready? We're going to watch it in 3, 2, 1, go. They all come in. Oh, that looks so nice. Look at that. I want to do the 1 over r squared force law as well. Yeah, let's just mess around with this. I'm super tired. Let's just mess around with this for a bit. I want this as my background, but it collides with my cursor. I can find a way. It's not a super nice visual. We can work on it. Wow, is that nice? I like how it's like, I don't even understand it, but I like it, Okay, we're gonna mess around with a couple of other things. Let me just copy this over. So let's go ahead and move test.mp4 into 2dr3 .mp4, and let me do the same visual except with the r squared force law instead of the force law that we just had to see if we get the same symmetric effects. It tickles my brain. Is it dampening? I don't think it's damping. I don't know. As far as I'm aware, there is PJZ here. There were some issues that at the beginning without dampening. Wait, what are we talking about? I missed something. Wait, who's PJZ here? Are they here? Let me go ahead and catch up on chat, by the way. I just missed a bunch of stuff. Oh, okay. So let's go here to... I knew you were here. You've talked in chat before. There we go. Is it damping? I missed it. I'm like super far behind. I'm so sorry. It is dampening. Yes, that is correct. That's why we have, it's 1 over r plus 1. Correct. I'm so sorry. I thought you were talking about damping as far as like oscillating, like, you know how you have like a spring that's going and it slowly starts to dampen, it becomes lower and lower. That's what I was thinking for dampening. I'm sorry. Softening, I think is what that's usually called, or that's what I had been calling it. I'd been calling it softening, not dampening. So it was just a linguistic problem. Let me run GNU plot and let me run the R2 force law with the cube and see what happens. What do we have here? You need a lot load off. I want this as my background. By the way, do you have any research of sensitivity to initial conditions for these simulations? Not right now, but I imagine there's a lot of weird chaotic behavior, which is something that we could look into. I mean, like, you know, maybe. No, it's not noob terminology. You're completely right. It was me just not knowing. I'm the one that doesn't know the terminology. All right, here's the R squared force law. Let me see what happens. They all come in. It's kind of doing the same thing, actually. Did I run with the wrong force law? I want to run the two of them side by side to see if we can even tell a difference. See, dampening is apparently the official physics term. So what's softening? Force equation. Softening. I don't think a lot of people know the word softening. I'd never heard the word dampening applied to this, but also, like, maybe I'm wrong. At least I hear it for the first time from you. Oh, okay, interesting. Yeah, right, optimal softening here. I think it's the same thing. It probably is the same thing. I just, let me see, dampening. So when I think of dampening of forces, I'm thinking of dampening of forces usually means, and this is what I don't know, but dampening of forces for me means you take F times exp of like some sort of exponential factor h or something, so that you have your traditional force or whatever, and then you dampen it off so that, you know, whatever the force was, let's say it normally peaks here or something. I don't know. It just means that it falls off further, right? So that's what I thought of dampening. Right, that's called dampening. But also, like, isn't the Yukawa potential the same thing? Isn't that like just the force of gravity times an exp? Oh, I've completely forgotten about this. Isn't that a dampening? I might be doing this wrong. I think it's Yukawa potential. It's been a long time since I did plasma physics, so forgive me. I'm super bad about this. Yeah, it's 1 over r with the exponential decay. That's all it is. So then you have the gravitational constant squared. And so, but this here, is that, I thought that exp was what's called a dampening. Okay, so I could be wrong. Like, I'm probably wrong about that, but I always thought that Yukawa potential was just the force of gravity with a dampening component. That's what I thought it was called. And I guess I'm completely wrong about that, which is totally fine. Let's see, what do we have here? I refer to, okay, I think it's the same thing. It's definitely the same thing. I'm being pedantic with terminology. When I was looking at the algorithm archive, so Julia is my main language, but I you know, we need to better advertise this, but obviously you can change languages, right? So if you go to Barnsley Fern here, you switch whatever language you want. Julia is just a language that I implement everything in, but other people implement it in other languages. Let's see, if you use a spring example. When an oscillating system loses energy, it's called dampening. You don't dampen the force, you dampen the amplitude, or at least I don't know how to dampen it. Look up n-body simulations on Wikipedia. It mentions softening. Right, that's, so to be fair, right, I don't, obviously Prutz isn't wrong. Like, I know, I'm almost positive people use dampening in this sense. Like, almost positive. Right, softening is a numerical trick, yeah. I like Julia, but I wasn't judging Julia. Just wondering. Screening is another term for that. Oh yeah, I've heard screening as well. So it's not a physical phenomenon. Dampening is right. So you're right. We're not. So that's why I initially was like, we're not using dampening, because I think that's the same like thing that I thought of. Right. I was thinking that softening is a numerical issue, whereas dampening is a physical thing, and we're literally just having a numerical. It's like a numerical trick or something like that to make it so the forces don't like hit each other. That's all we're doing here. I don't think it's a physical thing. Anyway. I don't mean to like, anyway, we're kind of rambling a bit. So let me convert this also to video really quick. So let's do Mogrify. And I want to play the two of them side by side and just see if we can, if we have an argument, or see if there's a difference between the two of them side by side. Okay, and so when we watch that, I think what I'm going to do is pause this video for a second. Okay, hello? Stay there. Okay. I'm pretty annoying in this chat already. Imagine how annoying I am at my job. I don't think you're annoying in the chat at all. I'm sorry if I'm giving the impression that you sound annoying. I'm chalking that up to the fact that I've been streaming for 4 hours already and I'm quite tired. And when I get to this mode, it's like everything's an argument when it's not an argument. Like, it's definitely not an argument. The conversation's actually quite good. Because, you know, I've been using softening to mean this like 1 over r plus 1 type of thing. But again, Shadipto here, you know, is the one that introduced it to me just a few days ago. So, you know, I'll do the 3D animation just a second. I want to play the two 2D animations next to each other. So what I'm going to do is I'm just going to cancel this guy for a second, and we're going to do MPV test. Where are we? Did I not? Oh, I forgot to create video. Okay, yep. MPV test .mp4. So we're going to have this guy play. Okay, so we're going to move this over here. Oh, sorry, I messed up. Okay, and then we're going to play the other one. MPV test, was it 2dr3.mp4? Stop. So it's going to be right here. Okay, so we're going to have them playing right next to each other. Let's move this back a second. So I'm going to try to, how am I going to do this? I'm going to try to preempt this one. Okay, so I'm going to play that one for a second, and then I'm going to go over here. Okay, I see. So over here. And so these are the two of them put together. Oh, so close to getting them like right next to you. Let me try that again. I was very close. All right, I'm going to, oh, stop it. I'm going to try to get them to play like right on each other. It's going to be kind of hard. Give me a second. Okay, so we're going to play this for a second. Okay, over here. Oh, it's pretty close. Okay. So over here we have r squared, and over here we have r cubed. They look identical. They genuinely look identical. I mean, did I think I know what I did. And you guys are going to be really upset about this. I think I'm plotting the same animation. I think I'm plotting the same exact animation because I forgot to remove the old data files. Okay, let me try that again. So I think it was just, yep, they're the same simulation. All right, let me give this a go one more time. And then we're going to do everything over again, and we're going to go. Oh man, that is definitely like Leos Labs fashion. It's just like, wow, look at this amazing thing. They look identical because they are. I've got some video audio desync. Let me fix that. I'm sorry about that. Here, there. Okay, that should fix it. Sorry, the video on audio desync came up when I was playing the two videos at the same time. All right, let me create the video here. Okay, yes. I can't believe that. Oh, I'm an idiot. If there's ever anybody on Twitch who's an idiot, it's me. All right, let's play this. Move this up over here. Should be fine. And now we're going to play this. Oh, no. Control C. MPV test. No, which one am I playing over there? R2... 2dr3.mp4. Perfect. Move this up over here. This guy. This guy. Move it back. Okay. I screwed up. Stop it. Shut up. Stop playing. All right, move this over here. Check video and audio. Desync seems fine. Okay. Play this. Go over here. Did I freeze? Okay. To be fair, they're not too dissimilar. Let's go back over here. Let's play this again. So this one over here is going to be our R2, and this is going to be our R3. So this is going to be the regular old gravitational force, and this is going to be our our 4D force. So I'm going to play this for a second. I go over here, and okay. So it looks to me that the only real difference is that the 2D force seems to go a bit faster. But the patterns are quite similar, which means the patterns are actually coming from a symmetrical argument, not from a like physical argument here. So these kind of like weird movements of the clusters here and there is simply due to like the forces that we're running. This is so much faster. Holy crap. Look how fast the one on the left is going. And it actually looks like now you're getting some sort of numerical instabilities causing like some sort of asymmetry. Yeah, okay. We must have run into like some weird floating point precision error. Interesting. Okay, cool. I'm happy with that. So now let's do the same for 3D. We'll use the, because Akris has been waiting for 3D for a bit, and let's just go ahead and get that done. So let's go over here. I'm going to move test.mp4 into 2dr2 .mp4. All right, perfect. So let's do it in 3D. We're going to remove the data file because we need to remove the data file. I just learned that. Otherwise, we run into really weird errors. So we're going to do gravity. Let's do 4D because we just learned that it makes it slower and dimensions equals 3. Here. Sure. Let's go over here, vi plot.jl. Oh, right. Remove this. I want something that's easily divisible by 3. Julia, what was 6 raised to the third is going to be 216. Let's do 216 again. Okay, run that, go over here, and then we need to do vi plot.gp, make these from -2 to +2. I'm so sorry. 2. Okay, write this, go over here, and then we should be able to just do... we should just be able to plot it, shouldn't we? GNU plot, plot.gp, give it a second. I hate floating point precision errors. Are you using Xterm everywhere? Yes, I'm actually using Xterm everywhere. That I recognize that a lot of people don't like Xterm, but I'm using it everywhere because I like bitmap fonts. And Xterm gives you bitmap fonts. That's why. Okay, let's give this a go. Let's do Mirage. Okay, here it is in 3D. Whew. Let's see what happens. All right, I'm gonna zoom in. Oh, that was nice. Look at that. Oh, that's pretty. I mean, I think the 2D one gave you better structures, but I really like the snowflake design here. That's actually like not bad. All right, let's mogrify this and get another video. Nice. How good is Xterm with copying a lot of text out of it, by the way? What do you mean by copying a lot of text out of it? For like just simple copying and pasting, you basically use like middle click and stuff like that, which is fine. Whatever that text buffer is totally fine. All right, so we're gonna run /create video. Yep, give it a go. At this angle, nice snowflake, very reasonable, very seasonally appropriate, right? That's what I did it for. Is it kind of hard to know whether... It is kind of hard to know whether the dots are blocking some others, though with a 3D sim. Yeah, this is inherently a problem with the fact that I'm using NuPlot to do all the plotting. Can you scroll, for example? I mean, look, I can scroll up, but the fact is if I open up a file, check dot something, check. So this, I can't scroll up here. So scrolling on a file doesn't work, but that's the only problem. Okay, so let's do mpv test.mp4. Let me full screen this guy. All right, you guys ready? We're gonna watch it in 3, 2, 1, go. I quite like it. I mean, it looks the symmetry here looks really nice. I want to redo all of my visualizations so that they're along, like they're all symmetric. I really do like this new grid look. It just, look, it's less physical. It doesn't look as much like a galaxy, but it looks prettier, and there's something to things looking prettier. This is good. Also, Shadipto, I have to say, thank you so much for figuring out the problem with the Force Law. Like, the fact that this is working now means that I have hope for the 4D simulation again. I genuinely lost all hope yesterday, and now I'm like, okay, I have hope again. This is pretty good. Let's see, it's currently the same as T-Mux. It looks amazing in 3D. I'm super happy with it. I'm going to do it one more time in 4D. So let me go ahead and move test into 3D R3 dot MP4, and we're going to do the same thing in 4D and see what happens. So what's 4D? Let me do one. I need to do one more thing. What is it? I need to do Julia. What is 6 raised to the 4? It's going to be 1, 1296. So let's do 5. 5 raised to the 4 will work. Yes, I need to remove it. You're correct. Thank you. So we don't run into the same situations. Like, oh, wow, amazing. Okay, I have to go. Good luck. See you, Press. Thanks so much for coming in. Hopefully you have a good time. You're doing all the heavy lifting here? I mean, not really. I'm the one that's running the same file over and over again. I'm like, huh, they look identical. Oh, man, that was so good. All right, we're going to do, we can either do 625 particles or we can do 256. Let's do 256 particles. 256. Well, maybe we should do 625. I mean, this is going to be a projection from 4D onto 3D. So we're going to have a lot of particles. How about smaller scatter? Yeah, we can do smaller size. Yeah, okay, let's do more particles, smaller size. You're correct. 625. Good. Okay, let's go here. Control D, vi plot.gp. And point size down here is 2, so let's try point size 1.5. And then we're going to modify this so it's -4, +4, see if that does anything. We might do yank 3 yank, paste it down here, comment these out. Oh, that did not happen how I thought it would. X range, Y range, X range, DD. There. And I'm going to set these so they're 2, 2, 2, 2. Just so we have that as backup, because I keep switching between the two of them. So let's do GNU plot again. Let's see what it looks like. I'm quite interested in the 4D one. I mean, look, we all know it's just a tesseract that's, you know, doing the same thing as all the other ones, but I don't know, it looks kind of prettier because you have more acceleration points and stuff like that. And admittedly, right, like, oh, LW is going to be messed up. I need to set LW equals 2. Let's do this again. And let me set L equals 2. Because otherwise this visualization is going to be wrong. Could not find file check.dat. Oh, because I removed it. Okay, let's try it again. All right, do it one more time. And then hopefully we get something pretty cool looking. And then we can go from there. But so far, yeah, I mean, look. We spent the whole day today just creating a grid of points, really. That's basically all we did. We updated the kernel and stuff like that. There's still a bunch of other things I want to do, which I guess we'll do tomorrow. Totally fine to keep working on this tomorrow. Like, the fact is, the big thing that happened today is we got the R-cubed force law working, quote unquote, which means, in principle, we have something that could be cool. We did a great job making those points. Yeah, honestly, we're getting there. Getting there one step at a time. Sorry if you heard something. I just slammed something on a desk over there. Okay, so that worked. Let's do Mirage. This is not a tesseract. I'm like 25% sure. That's not a tesseract. Ooh, maybe that's a tesseract. Okay, wait a minute. Is that a tesseract or not? I cannot tell. We need to zoom in a bit. But it doesn't look like a tesseract from here. Now I can't tell. Are we... All right, let me zoom in. Yeah. Plot.gp, let's go to this set again. Okay, let's go here to GNU plot. Let's try it again. Darn. Okay, that's fine. Let me get some water. Okay. Maybe lower the amount of points. Yeah, I need to do that as well. I was going to try to zoom in to see if that helps us, but I think a smaller number of points is correct. Or we change the point size again to be a bit smaller. It might have kept rounding up. Let's drop the point size. See if that does anything. Oh, it's taking longer to plot because we have more points. Right, and because we have more points. Okay, I see the problem. So we're going to go into Mirage, zoom in here. I'm not convinced that's a Tesseract, but I'm not convinced it's not a Tesseract. It might be. Okay, let's plot.gp, change the point size down to 1 here. And now we're going to do GNU plot. So I think the Tesseract should be like a small cube in the center with a larger, kind of, like, it's a cube within a cube is what you're looking for. Like, that's what we're looking for. A dense center with, like, a less dense outside thing. Just do 16 points. That should look like a Tesseract. Correct. That should. Okay. Let's redo it with 16 points. Remove here. Let's just check it with 16. I'm an idiot. I'm a complete moron. 16. Let's go here. Plot.gp. We're going to make them big again. Point size is going to be 2. Okay, now we're going to run GNU plot. Should be pretty quick this time. I mean, we only have like 16 particles we're plotting. Seriously, I am having some trouble right now. Like, words are not coming out of my mouth. Let's do Mirage here. That, I can't tell. We have a square. I mean, look, I think it's correct, but it's kind of hard to tell because we're so far zoomed out. Let me zoom in a little bit further. Plot.gp. Let's just go to -1, 1. GNU plot. I think it does look correct. Yeah, I think you're right. It looks more like a Tesseract than 3D Cube for sure. Yeah. Okay, I'm just going to zoom in just to be sure, though. So let's go Mirage. I mean, okay, I think that's right. We have 1, 2, 3, 4, 5, 6, 7, 8. So that's our center cube. No, wait, where are we? What are we looking at here? So 1, 2, 3, 4, 5, 6, 7, 8. And then we have 1, 2, 3, 4, 5, 6, 7. 1 second, I'm bad at this. This is our center cube, right? That looks like a cube. It looks like from this angle, it looks fine. I just don't know what's happening with these dots here. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wait, what? How many points do we have? 1, 2, 3, 4, 5, 6. 12. 12 plus 4. 1, 2, 3, 4. Okay, this looks correct. The far diagonal points and close diagonal points are just overlapping. Yes, you're right. I should zoom around really quick. But I think this is right. I mean, it looks right to me, I guess. Okay, let's increase the number of points again. So we're going to do... But to be fair, like, it is quite... I was expecting... Yeah, why are we so far zoomed in? Oh, probably because L2. Yeah. Let's set L equals 1.5. Yeah. Gotcha. Let's set L equals 1.5 to project it so the wings are further out. Fortunately, I can't change the angle of view with that one. All right, so now we're going to go to GNU plot. And so this should make it so the particles are further out, and this should allow us to better see it, I think. I don't know. I can change the angle of view with GNU plot. I've done this before. I can figure it out. Give me a second. I can figure it out. Mirage here. Okay, so this projected differently, and we should see... Okay, come on. So we should see, here's the initial cube, 1, 2, 3, 4, 5, 6. And then I think this is right. I mean, let me change the camera angle. I think I can. I just don't remember how. So let me go into the iBacka directory. Where am I? Back one more directory. Simuleos, affine, transformations. No. Crap. Plot? Oh no. Okay, let me figure it out. Yeah, I can. I've done this before with GNUplot before. Let me just see what I need to do. CD projects, Simuleos, affine transformations, ls here. Oh, that's why. Okay, so we have rotate cube.dat. We have semi-rotate. We got scene. Oh gosh, this code was awful. Videos, all these PNG files, Mirage, out, dot, 000.png. What was this? So this should be a rotating. Yeah, okay. This is what I'm looking for. Perfect. So here, if you look at this, you see we have a cube and it's rotating, and that's all it is. It's just rotating up here. So I should be able to change the axes with GNUplot. I just have to figure out how to do this again. So I need to look at the plot script. ls_.gp. We have check.gp. We got check.gp. Was it all just in check.gp? Is that what I was running the whole time? No way. Oh god, it's been such a long time since I ran this code. Set view is what I want. Set view, I guess 0021. And then every time step I was just changing the view. Oh man, that was the most difficult GNUplot script I'd ever written. Like I don't mean to like. The hardest video I've ever made in my life was the video for affine transformations. It was so incredibly difficult, like just insanely difficult. Crap. Let's go here and let's do videos. And then this video right here for affine transformations, the absolute hardest video I've ever made in my life. Like, not because the content was difficult. The content was pretty easy, but the visualizations were super hard. I had to use like 5 different plotting tools. It was just insane. Absolutely insane. And look, I mean, a lot of people seem to like the video. I mean, it's, you know, decent enough, but man, I just don't think it was, I don't know if it was worth it. Okay, so we're going to change the view here to be that, right? This. So I think this is 0 and X, 2 and Y, and 1 and Z, I think is what this is. Let's write this, go over here. And now let's run GNUplot. I think this will change the view, and I think we can go from there. Okay, give it a second, and then we're going to do Mirage. Okay, so we're looking from the top view. So here's the cube, and then here's the points. So, yeah, fine. I'm happy enough to say that this is probably a tesseract then. Good. Okay, so let's do it again in 4D with more points. Why are you streaming software and game development? It looks correct. I'm not streaming on software and game development because I'm not writing software or doing game development, so it doesn't seem like the right place to stream. I mean, I'm not gonna, you know, let me move this up here. And this up here. Perfect. Run this. Okay. This is software. No. This is, I'm doing programming, but I'm doing research. There's a key difference between like writing software and doing using software to make things, right? Sure, I'm writing code. I'm using programming to do the research. But you know, science, tech, it's research. You know, we're doing stuff that people haven't done before. And sure, I could go on software and game development, and I reckon the stream would actually do quite well in software and game development. But what I'm actually trying to do is change the tone of the science and tech channel, science and tech category. So it's people doing fundamentally new research, whether that be in, you know, computer science, physics, bio, chemistry, math, whatever it is. I just want people to stream their research and stuff that people haven't seen before. And so the point of the stream is to find a way to make this research open and engaging and interesting for a bunch of people. And so, sure, yeah, I'm definitely using code, but I definitely don't feel like I'm writing software. I mean, to some extent I am, but I don't feel like the purpose of this is not to write software. The purpose for this is to do something fundamentally new that people haven't done before, right? I mean, we're doing a 4D Galaxy sim. In principle, yeah, I think I could do pretty well in software and game development. I think the people who watch software and game development could very much enjoy the stream, and I think they would very much enjoy the stream. But I'm primarily trying to do research, right? The algorithm archive is arguably software goal. Yeah, but it's also arguably research goal, right? Like it's the same way how academics like write textbooks and stuff like that. It's like, you know, if you're a PhD or you're a professor somewhere, like obviously you want a textbook to go with your classes. So I agree that you could argue the algorithm archive is definitely software, and I accept that argument. So maybe I go to software and game development for that. But the real reason I'm not on software and game development is just because I feel I fit better in science and tech. We can make all these arguments about how the people who are going to watch my stream would probably be on software and game development, not on science and tech, all this kind of stuff. But at the end of the day, that's how I feel. Two categories do overlap, so it's not surprising that people think it should be on one and not the other. Yeah, I also agree with this completely. Which is why, like, when people say, why aren't you here? I've made a bunch of arguments for it one way or another, but like, why aren't you in software and game development? I've made a bunch of arguments one way or another, but that's just how I feel. And you kind of want to have everything in the same spot for simplicity. Right. I do agree with that as well. Which is why, again, I'm hoping that the science and tech category on Twitch will slowly start to evolve. So now that we don't have the programming or the software and game development channel or category inbuilt into science and tech, and we don't have the animals in science and tech anymore, I think we can grow science and tech to be a community exclusively for researchers who are doing their research live on Twitch. And I think that'd be phenomenal. I'd love to see that. And so I'm really pushing for that, like really pushing for that hard. And we'll see. I mean, maybe it doesn't work out. Maybe in the next few months, I'm still the only one. I'm not the only one now, but in a few months, I become the only one who's pushing for this type of thing. Maybe science and tech dies. Fine. In that case, I'll move to software and game development. It'll be fine. I'm not too worried about it. Okay. So what was I going to do here? We took a look at that. Let me run this one more time with more particles here. And let's see. What do we want? What did we have before? We had like 216, was it? Julia. Let's do 5 raised to the 4. So let's do 4 raised to the 4. It's going to be 256, obviously. 256. And we want to run that with L equals 1.5 is probably fine still. Yeah, let's do 1.5. Yeah, we're doing 625 before, but I thought that was too many points, so I dropped down to 256. Okay, good. So now let's go ahead and try plotting that. We're going to do... I need to modify it. VI plot... .gp. So let's no longer set the view here. And now let's run GNU plot. Okay, and then we're going to take a look at this. And then, honestly, I think we kind of need to wrap up for today. I've been streaming for 4.5 hours now. It's 7:30 my time. Actually, if I'm honest, I've got a call with my grandparents in about 30, 45 minutes. Something like this. I don't know. I need to double check the exact time, but it was scheduled to be 30 or 45 minutes from now. So I kind of need to wind down a bit for that as well. So let's do Mirage here. Okay, the Tesseract's a bit big now, isn't it? Okay, so let's zoom in. 1 second. Is it all on GitHub? Not yet. I'm going to push the latest changes in just a second. We need to zoom out a bit, don't we? Let's go here to viplot.gp, and let's comment this out here, there, and then this. Break this, go over here, and plot it one more time. So let's run GNU plot, and let's see what we got. So as far as where we're going to go, there was actually a bunch of things I wanted to do on today's stream that we didn't do. We just frankly did not do. We're going to zoom out and see what that looks like. Like, for example, for the performance measurements and stuff like this, like we just didn't do that stuff. So I'm going to talk about what we didn't do and what we still need to do and kind of the timeline for getting that stuff done. So let's do, where are we? Mirage. Here we have this. Oh, why are you all the way over there, dog? I need a new GPU. Let me go here. There. Okay. Good. So let's take a look at this. And let's do it. So here's our Tesseract. Zoom in. I think that looks pretty nice, actually. I mean, it looks a lot like the 3D sim, but I actually kind of like it a bit better. So let's go to this. Let's do Mogrify. Where am I? What is going on? I'm just, for some reason, on the wrong everything. Okay, there we go. Mogrify. Let's give it a go. And then we'll take a look at the video. And let's talk about what we need to do, because there's a lot of little things to do. Let me go over here really quick. Let's see. Go down. I think with the symmetry coloring the points based on W would actually make it look nice. I think so as well. But I don't know how to do that right now. It probably could with GNU plot, but I'm fundamentally limited with that. There's a lot of other things that I want to do as far as writing to file, and we'll talk about that in just a second. Yes, here. And we should have a video. So let's do MPV test.mp4 and let's watch it. All right, we're gonna play it in 3, 2, 1, go. All right, so you see all the particles come in. We see some of them fly right out. And part of that is because of the projection that we're doing. Again, this is a 4D simulation projected down to 3D. So you'll see that kind of the wings outside of the cube at the center are kind of like very far spread out. So anything that kind of goes in that area is just going to zoom out really quickly. But this looks really cool. Like, sure, there's some things that we need to update, like, but you can see the tesseract structure as well. It's actually really nice. I quite like it. We still need to figure out how to visualize it. There's still a lot of things that we need to do. But it's slowly getting there, and I'm happy with this. Yeah, that looks pretty good. So let me go ahead and move test.mp4 into 4dr3.mp4. Perfect. Wow, okay, this has been pretty good. Let's go ahead and do cd backer directory. Git status dot git add dot git commit. Right now the points don't collide. As they get closer and closer, what we do is we change the force so that it's slightly less than it would originally be. We basically add a 1 to the 1 over r squared so that as they get closer together, they don't just zoom right past each other, right? Kind of cool that it seems like a bunch of the points are fairly stationary. Yeah, that's the reason they're so stationary is because it's a 1 over r cubed force law. And this makes it so they don't see each other as much. So as the particles are super far apart, they don't really see each other that much. Fixing 1 over r cubed. What else did we do? Lots of things, but what did we do? We changed it. Oh, and adding grid init. Sure. Git push, origin, development. All right, let's go. Okay. So there's one other thing to talk about. So really quick, let's go to github.com. So if you're looking for the code, oh, that could also be true. I think Shadip does right. So let's go here and let's go to galilee.jl. So if you're looking for the code, feel free to go here. I'll go ahead and give you guys a link. Oh, sorry. Here. Now, for the record, everything that I'm putting... Oh, you're kidding me. Everything that I'm putting down is in the development branch. So to do this, you need to go down here to development. And here, let me just give you guys a direct link there. The reason I put it in a development branch instead of the master branch or main branch is simply because... I don't want people like randomly going to the code who aren't watching the stream and aren't on YouTube and all this kind of stuff and being like, what is this for? It's kind of a crappy code base. Like, it's in development, right? And I just don't feel like I want stuff publicly accessible outside of you guys, like people who are not watching this stream, who are not watching it live. I just don't want people to see all of the mess that goes into that on the main branch. It's just kind of how I write code. I always like to put it on a development branch. Anyway, so... what are we doing? So let me go ahead and go back over here to XernalPP and let's go to talk about what we still need to do. I think it's probably up here at the top, honestly. Right. So at the very start of today, okay, now we're into stream. We talked about doing a second method for parallelization here. We never did that. We still need to do that. So this is one thing we need to do. There's a couple of other things that we need to do. Journal, new page before. So one, we need to talk a little bit about performance. So performance things I want to check. Okay, so one thing is going to be axis swapping. The reason I want to do this is I realize that the way in which we're accessing elements, it's primarily along like X, Y, and Z, not along particle-particle. So by swapping the axes, we get a coalesced, a better memory access pattern by switching the X and Y axes. The other thing is I want to try using parallel sum for... force integration or acceleration integration. Okay, so these are things I need to do. Other things that we need to do. Obviously, there's a lot of galaxy-specific things, dark matter, black holes, different mass of objects, all this kind of stuff we have to add in. But for like what I'm looking at for the immediate near-term goals, we also need to look at file I/O. Now, the reason we need to look at file I/O is because, frankly, right now, the plots are kind of garbage. We're doing them in NuPlot, and I'd like to like bin all the data into one giant image. Now, to do that, we are going to run into some small issues here dealing with, we can only deal with up to like 4,000 particles on my 970. So for that, I do have access to other like clusters and stuff like that I can use. So in addition to adding an additional file IO method for like outputting directly to image, I also want to work on other clusters and stuff like that and figure out how to do that on stream. Some of that's just like masking the IP and all this kind of stuff. It's pretty easy to do, but some of it is a bit more complicated than that. So 3, we also need to actually start working with the Barnes Hut. This is hopefully going to happen soon, because frankly, it's embarrassing that we haven't done it yet. We've been focusing exclusively on n-body, trying to optimize that result as best as we can. And the reason we've been doing that is because we want a really good benchmark against the Barnes Hut scheme. Now, I have a lot of papers on how to optimize the code for Barnes Hut, how to do this in parallel. But I just want to get that implementation down, make it as fast as possible, and really just benchmark it, see where we're at. And all that kind of stuff. Heathers, thanks so much for following. Really appreciate it. Okay. So the Barnes Hut, for those of you guys who don't know, is basically another like clustering method that we can use to better do the n-body simulation. Little Math Boy, thanks for following. Really appreciate it. Okay. Once we do Barnes Hut, I actually want to look up at other clustering methods. I am super interested in not only k-means, but also really interested in affinity propagation. Now, look, affinity propagation is one of those things that it's bad. Propagation. It's really bad memory efficiency wise. But it might be nice for other reasons. So this is something I want to look into as well. And let's see. Do you have access to some HPC machines? In principle, I still have access to the one at MIT. I'm not going to say which one, because I don't want anyone look, we have 56 people watching. It's not like there's going to be a DDoS attack on it. But this is something that I'm interested in doing. There's no chapter on k-means. If we end up going down these routes, I will make chapters for k-means and affinity propagation as we go into them. So these are 2 things I'm quite interested in. And then we also have, 5, which is just making it more physical. So dark matter. And then we have, black holes. All this kind of stuff, just to make it so we can get the results. And then finally 6, we want initial conditions. So the reason this is going to be interesting is I'm not sure if any of the initialization routines, I think we're just going to have to let the simulation run for like a month, because what we're looking for is like some weird spontaneous symmetry breaking, essentially. Like, where does that angular momentum come from initially? Like, how do we go from a 3D mass into a 2D disk if we don't initialize it with angular momentum? And the answer is most people initialize it with angular momentum. So that kind of makes this whole double rotating galaxy here somewhat trivial, right? Like, because of course, if you just add angular momentum this way and this way, it's fine. The 4th dimension here is another spatial dimension here. It's not time. It's literally another spatial dimension. So we're talking about 4 spatial dimensions in a single simulation. Won't it be dominated by floating point errors? Right, but we're relying on those floating point errors to incorporate or to create the symmetry breaking. Do you intend to use it, HPC machine, to create some animation for the simulation? I'm hoping to. I will use it if I feel like there is some significant research interest here. I kickstarted my own with angular velocity, so much easier to get a nice disk. Right. So the question is, can you do it without the disk? Okay. So now I want to talk a little bit about research. So here's where my current research interests are in this. So the first is higher dimensional octrees. Higher dimensional octrees. But there's something else that I want to look at before we leave, which has to do with something that someone mentioned here, dealing with, what was it? It was relativistic effects. How to do these simulations efficiently would be quite interesting. 3 here. So floating point errors act kind of like quantum fluctuations did in early universe. Maybe something like that. But yeah, something like this. Okay, so we want higher dimensional octrees, relativistic effects. I'm quite interested in, again, the k-means, affinity propagation, speeding up the simulations here. That's what I'm really interested in. Getting that disk animation as fast as possible. This is kind of what I'm looking for. I'm not sure how you'll model dark matter in 4D. General relativity uses 4D to model motion in 3D. So 4D would not need updated 5D relativistic equations or misunderstanding dark matter. I don't know dark matter super well, but also we'll use 5D is what we'd have to do. Absolutely wild thought. Do you think brain-computer interfaces will allow us to visualize higher dimensional spaces? I don't know. I genuinely don't know. But you're talking about more like VR type of thing. What I feel like we're still inherently limited by the 3D space. Like even when you look at a 2D plane, you're imagining a 3D space sometimes. Like when you look at me, you're imagining I'm in 3D, right? Like you're filling in the gaps and making me 3D. So it's not really 2D. It's 2.5D in a way, right? And so doing a full visualization of 4D, I feel like putting it on a 3D screen doesn't necessarily help too much because we're already visualizing it 3D. So I don't know. It's an interesting question. If you practice, you can get better at it though. Right. Yeah, that's true as well. Okay, so these are things that I'm interested for research: higher dimensional octaves, relativistic effects, as well as simulating those effectively. But then I'm also interested in taking this a step further, dealing with the color quantization and computer graphic stuff, and specifically focusing on using color quantization, which is basically using the same methods for better photomosaic. Again, I'm just writing all this down so we have it written down. From the photomosaic, I actually want to go into ASCII art. I know this is kind of weird. I know it's super far out. I'm just mentioning this. And then from ASCII art, I want to go back to fractal compression. And the reason ASCII art is actually interesting, I'm going to mention this here, is because this is where we actually bring in shape matching. Oh, I love shape matching so much. It's amazing. And then we go from here, we go back to, with all this, we have a good understanding of how we can model physical movement through essentially an affine map is what I'm looking for. That's why I'm interested in shape matching. So then we go from here. I'm sorry, I'm just rambling here. I know I'm rambling. A lot of people don't know what I'm talking about. And then we talk about fractal compression before we finally go back to physics, where we do n-body simulations on a fractally compressed grid. So we basically physics on a fractal compressed grid. Physics on a fractal compressed grid. Okay, so I wrote all this down so you guys kind of understand what we're talking about. Yeah, higher dimensional octree, yeah, obviously like hexadecactree or something like that. So let me just kind of jot this down a bit. So this stuff immediately we can do this week. I think we can do these within the next 2 weeks. The other clustering methods might take about a month, and this will probably take 2 months. So we're looking at this whole thing being done in roughly 2 months, I think. That's kind of what we're looking at here. Then for this stuff, the relativistic effects, all these kind of stuff, if we want to look into these will also take about a month or two. The color quantization, this will take a month, another month here. This will take probably 2 months. And then finally we have this guy, which will probably take about 3 months. So we're talking about putting it all together, like basically the entirety of 2022, like done. For ASCII, what does the end goal look like? Essentially what I'm looking for is a fast visual representation of 2 different types of ASCII art. One is a density-based form. So let me just go ahead and do MPV, CD MPlayer. What do we have? MPlayer, videos, Arcane, Algorithm Archive Introduction. And let me just play this. Oh, sorry. Let me just play this for you. Sorry, I need VOCACA. Okay, here we go. So there's this type of ASCII art. Let me full screen this guy. Oh, okay. I guess I can't full screen it. So there's this type of ASCII art, which is just basically, hey, there's me as ASCII, right? This is fine. We already have a real-time ASCII renderer. That's not so bad. But what I'm interested in is actually combining this with other types of ASCII art, like for example, SL. This is actually a structural based ASCII art. So the idea is you have like the outline of a train that's been warped to fit the ASCII glyphs. And the reason that's actually interesting is because it involves a type of shape matching. And I think by combining the two, I'm interested in both, right? I'm interested in the generation of faster photomosaics because this solves a histogramming problem. Oh, actually, that also brings up some other stuff that I didn't even mention. Oh, wait. We have more stuff to talk about because actually I'm quite interested in another set of problems. Let me go here. I'm also interested in these because they help solve the histogramming problem. Gramming. This is useful in both the file IO here, but also in the ASCII art, the photomosaic. And then the shape matching allows us to better find like ASCII maps and stuff like this. So anyway, I'm super interested in making high definition ASCII art is what I'm interested in doing it. That's what I'm interested in, whatever high definition means. Let me go ahead and catch up on chat. I'm missing a lot of stuff over here. Higher dimensional octree, wouldn't that have some other meaning? Yes, it does. We can already visualize them if you treat color, smell, touch. Right, maybe, right? Like, but what would a smell dimension look like exactly? What does a smell dimension smell like, I guess? Like, because you don't have like, I guess you have like stinky, not stinky, right? But like what, I don't know, like what does that mean? We can already visualize them. For ASCII, what does the end goal look like? By the way, if you're looking for a volunteer for writing up some of the algorithm archive book into LaTeX files, harder if you want to present all the programming languages, and be willing to help with that. Seems like a cool project to be part of. Yeah, I'm super happy with that. So right now, we have... Right. So the big problem with that is what we want to be able to do is bind all of the chapters together into one printable book. That's what we'd want to go with there. So the idea would be like you'd want people to be able to select Julia and the languages that they want to bind together. And if you could bind that into a PDF, that would be amazing. Because then what people could do is just say, hey, I want to learn computational physics with Julia, and just select the things that they want, or like select Fortran or whatever. That'd be super cool if you could do that. But otherwise, the LaTeXifying, I'm not sure exactly. Okay, no, that'd be super cool if you could do that, actually. But I'm not sure if right now we need to update with LaTeX or not. PDFs can hold JavaScript. That's fair. That's a fair argument. We can talk about it. Also, might consider modified Newtonian dynamics as an alternative to dark matter. Might be easier to implement and appears to account for galaxy rotation. Oh, now that's useful. That's something I didn't know. That might be what we want. Yeah, let's give that a go. I think combining the two will make better ASCII. So you can do that. You can do that. Why would you increase the dimensionality of an octree instead of just using KD tree? Do you want a bunch of leaf nodes with no useful info? Yeah, so that's the question, right? We'll probably be using a KD tree, but the sparse octree representations have some good. They have some good reasons to be used, right? And so I'm interested. That's why I'm interested in it. I'm just interested in seeing like, is there actually a need to do this beyond higher dimensions besides memory locality and stuff? So PDFs can hold JavaScript. You can do that relatively easily. Is there an issue that is documented with this goal? There might be, but it might be super old. Would that be in the file or outside of the file? Like, would you pick it inside the PDF or picking a specific PDF file? I think like binding a specific PDF file is what I think. You can even do that in sconce thingy. Oh, really? At least picking the outside of the file. Yeah, I mean, if we can just do that with sconce, that'd be super cool. Anyway, so to be fair, I don't think this one is going to go anywhere in terms of research projects. I don't think this one's going to go anywhere in terms of research projects. I think the cool, interesting projects are going to be better histogramming methods, if we could do that. I don't know if we can, but if we could, that'd be amazing. And like, you know, different things like this. So that's kind of where I'm going with all of this. I just want to like write this out for everyone so everyone kind of sees like what I'm kind of thinking with this. Let's see. I did my internship report with Gons as a build system. Oh, really? That's super cool. Okay. So let me go ahead and just erase a lot of these dashes here, and just kind of leave the text up. And I might just screenshot this, and I might just have this available, just so I have it saved somewhere. There we go. Good enough. I did my internship report with Gons. Okay. Let me just go ahead and put that on Discord so it's just there, just because otherwise I'm going to forget. Also, if you haven't already, here's the Discord link. Go ahead and giving you that. Upload a file, screenshot, open, just pasting that there. Just research plans, sorry. Okay, that's just what I want to put, just so it's there. Just so I remember it's there, I can look at it later. Okay. But I do think that's it for today. Since it automatically runs exactly as much as needed, it's less time consuming than a Makefile. Oh, that's interesting. I hadn't thought of that. Okay, so I think that's it for today, guys. Let me go ahead and go to Twitch, see who's live. Lana's live, Dr. W40, Tim is live. If there's anybody in particular you want to raid, feel free to let me know. Otherwise, I haven't raided Tim in a while. We raided Lana just a few days ago. So I feel like raiding Tim would make the most sense here. Yeah, maybe raiding Tim. I think 40 would be Hypertree. Yeah, I think you're right. Anyway, thank you again for streaming. Yeah, thank you guys so much for coming in. I really appreciate it. If you guys don't know, this is Laos Labs. The entire point of this is to create open, engaging research for anyone who's willing to listen and anyone who's willing to hang out, you know? That's the idea. And so I really like the idea that we can, you know, hang out, chat, talk about cool things together, and just, you know, do research in a way that research is meant to be done. I mentioned this at the start of stream, but I'm actually going to be probably revising the YouTube content I'm going to make in the next few days or next few weeks or whatever. so that it's more focused on like the act of doing research and not the results of research itself. And sure, we'll do obviously stuff on the results, but like I just showed, it could take like 2 months before any of this is actually done. And the way I see it is, it's just not like, it's not, there's no way I can wait 2 months for another YouTube video, right? So I think doing more like an episodic type of thing makes a lot of sense here. Alex Thunder, thank you so much for following, really appreciate it. And I think that is it for now. So let's go start the raid on Tim. So here we do raid, Tim, Beaudet. I think that's correct. I missed a U. Beaudet. I think that's right. Okay. Thank you guys so much for coming in. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. I'll be live tomorrow at 2 o'clock Central European Standard Time, and I'll be streaming until about now tomorrow. So it's from 2 to 8 tomorrow. Feel free to join if you want. We'll be continuing working on the 4D simulations, making them a bit more efficient, and working on this top list of things. What is it? Shift. This top list of things here. This is kind of what we'll work on tomorrow, and then hopefully we'll do File IO after that, and then move our way into the Barnes Hut stuff after that. There's lots of little things to do. We're still like months out from this actually being done, but slowly but surely we're getting there. Anyway, guys, thanks again for coming in. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. I'll see you guys around next time for the next episode of Simulayouts, where we do hopefully more cool stuff together. Really happy with that. See you guys. Bye.